in the Institute of Zoology. So I'm basically a mechanical engineer, but since a lot of times I'm working on in biology and by inspiration for robotics. Since many years, we try to understand the principle of bipolar and quadruple locomotion by using, let's say, very complex experiments in animals combined with different types of and very complexities of different models. These principles are basic strategies, so we understand as basic strategies in order to have agile, stable, and economical locomotion. And today I will try to discuss these principles and what is similar in bipolar and which is not similar to quadrupedal locomotion. And as example of bipeds, we use birds, apes. And in the boundaries between bipolar and quadrupedal locomotion, I will introduce our examinations on the Japanese macaques. And finally, I will talk about dogs and rat locomotion as example of quadrupeds. So let's start with avian locomotion. So why avian locomotion? Actually, the birds are the most successful bipeds in terms of diversity. You have about 10,000 species of birds, and most of them are able to work bipolarly very well. And there are about 80 to 100 species of grounded birds, which partially or totally lost their ability to fly. So you have a very great variability that you can use in order to understand locomotion. For example, you can have geometric similar animals and you can analyze the influence of mass on locomotion. Or in the case of these waders, you can have animals which have a similar mass, similar ecological niches, but they have completely different segmental proportions. And there are other things which are interesting in birds. For example, they use gaits that we don't normally use as humans. So they have, for example, a grounded running, which is a running gait, but with double support phases. So which things that we don't normally use. So it's a running gait because the mechanics of the center of mass, potential, and kinetic energy are in phase, which is showing running mechanics, but you see they have a double support phase. And one of the most important things for me was the body plan of the birds. They are completely different from our body plan, and they use a so-called pronograde trunk, which means basically parallel to the ground. And in that case, is the center of mass not above the hip, but in front of the hip. So this produced that in order to have stability and the tools are below the center of mass, the femur is horizontally oriented and not vertical like in our cases. And the second thing is that they mostly keep the femur fixed and they use the knee as a main retractor of the leg. So you see they have a zigzag leg, and if you combine this pronograde trunk and zigzag leg, you will think this is a more costly locomotion than humans if you have vertical and straight legs. And when we start, there was some kind of meeting that's, for example, that the femurs did not move at all, or that grounded running, for example, is an artifact of a treadmill locomotion. So we were really interested what are the advantages of pronograde trunk and why they have these zigzag legs. So in order to understand that, we started about 10 years ago first experiments on quails, and we use biplanar X-ray fluoroscopy combined with ground reaction forces in order to understand the dynamics of the motions. So we used the quail, which is just the smallest chicken in Europe. It's about 200 grams to 400 grams. And we were, of course, interested in this guy because they fit well in our facilities. And second, if you're really small, almost every substrate is uneven. So you need a very, very robust strategy for locomotion. By analyzing these guys, we found three main strategies to obtain stable chronograph locomotion in grounded environment. So these three strategies, we use it in a model to show that these strategies produce stable gates. The first strategy we found is that they fix before touchdown, about 30 milliseconds before touchdown, they fix the angle between the legs. The second strategy we found is that they use BPP control for trunk balance. That means that the ground reaction forces are directed to a point above the center of mass. And in order to have this change in the forces, they have a hip control. And we will see that how it works. And the third one is that they use an asymmetric leg behavior. So they have long legs at touchdown and short legs at two off. So this means that they are absorbing energy actually in the legs. So, and we model that in with massless legs and spring damping system, in which we optimize the parameters to fit the leg function that we found, combining ground reaction forces and the change of the leg length. So you have an effective leg that we call that from the hip to the foot. It's a model leg, which is like a spring damping system. And this leg generates an axial force. And in order to change this force to the BPP point, you need a tangential force, which is produced by the torque in the hip. If you produce that in a model, you can get a very, very stable solution. So this model don't have any feedback control, and it's able to cope with uneven locomotion. And just by using these three strategies, aperture angles, spring damping legs, and the forces going to ground reaction forces, which are going to the BPP point, this blue point above the center of mass. And what we are doing now in this case is we design a robot based on this idea we call eNandu, and we are building up this robot right now. So we expect to have first step of the robot by the end of the year. Okay, going back to the leg function of these birds, if you have an effective leg function like works like a spring damping system, you have to generate this function somehow in the joints. In order to understand that, we made some inverse dynamic analysis on these quails. And you see this is our hip joint angle. You see that the hip joint angle does stay, but it's a little bit higher at the end of the stand phase. And the second one, this is the torque on the hip joint. And if you combine both, will become like a working loop. And in our case, if the working loop starting on these circles, it's rotating to the right, is a positive one. So it's give energy to the system. In the knee, you have a thin positive, and in the last of the joints, which is a tarsal, metatarsal phalangeal joint, you have a negative. So you have like a damping system. And the intertarsal joint, which is similar to our ankle joint, we see like more like a spring behavior. So you have all these behavior that you need for the for this effective leg, but they are so split and on the joints. And if you have that kind of behaviors, how they control the kinematics, how do they have a function to produce the kinematic based on this effective leg? So we ask this on these three guys, which are waders, and they have similar mass, but they have different leg proportions. So we ask how they to control the joints. And of course, if they have always the same kinematics, means that there's one control, but they don't have the same kinematics. So they must be optimizing something, we thought. And we made a very simple model to find that. So if when in most of the stand phase are the tools on the ground, so they doesn't move, to have only 3 segments which are moving. And if you join these segments with the effective leg, you have a 4-bar mechanism, so you have only 1 degree of freedom that you have to optimize. And we did that with optimizing the hip joint. And we said, of course, we cannot optimize torque because we will get a stride leg. So we thought we will have to optimize or to minimize the work on the joints. And we did that. And if we look at that point, if you have, if you use in the intertarsal joint, yes, you don't use like elastic recall that we know that this work like a spring system. The result of the optimization are straight legs, so straight tarsal metatarsal with a tibial tarsus. But if you set some energy recovery in this joint, like they have actually, what you see in this point, 0.6 energy recovery, there is like a bifurcation in leg configurations and change to a zigzag leg, the crochet posture, and this is minimize the work if you have at least 60% of energy recovery. And we know from works on birds that they have at least 60% of energy recovery on the intertarsal joint. And this is very interesting. And if you are like an opposite in which you have a very short femur and a long tibial tarsus, you don't even know any energy recovery to have minimize the cost of locomotion with crunched legs. So if you have a pronogoid trunk and you can save energy in the tarsal joint, the crunched posture minimize your locomotion. And afterwards, we were of course interested what happened when they fit or when they face sudden drops, for example, or when they, which is different with visible drops and sudden drops. And we have another type of perturbations produced, and this is what I will show you today. This is step perturbations, and from these step perturbations, I will show today step-up perturbations. And we have our setup was, we have 3 different highs on these perturbations, and this green is 1 centimeter, red is 2.5 centimeters, and blue are 5 centimeters. So it's about 10, 25, and 50% of leg length. So on, we had also include force plates, and we analyzed again effective leg, the joints, and also 3D counting angles from pelvis and also from the leg. And what you see now is quail negotiating 1 centimeter perturbation. It's like nothing for them. So now we change to 2.5 centimeters, and they can make it even if they have an egg inside. So again, and if you have 5 centimeters, so 50% of leg length, they still can do it. Yes. So how is the strategy to cope with these perturbations? What's most interesting is that the quails, after 1 step, they regain steady state locomotion. So what happened? So in black lines, you see this is a level locomotion, unrestrained locomotion, and in green you see now 1 centimeter step up locomotion. Basically, the functions on the joints doesn't change. The only thing we can find is that in that case, the knee and the intertarsal joint are a little bit more flex it at touchdown, which are the vertical lines we see, for 2.5 centimeters. It's again, you see no change basically. The only thing that changes is the intertarsal joint extend a little bit more. So they have a little bit more input of energy. And if you have 5 centimeters, in the leading limb, we're talking about the leading limb, the leg which is stepping on the perturbation, again, you don't see much difference at touchdown related to the other ones. And the only thing you see again, the intertarsal joint works more like a motor than it's not working anymore like spring. But what happened? What they're doing actually? The strategy that they use is that they try to step up with the same parameters that they normally use in label locomotion. So if you look also to the effective leg, they use the same angle of attack, the same angle between the legs, and almost the same leg length. And with that, they can regain very fast the locomotion, so steady state locomotion. What actually changed is the trailing limb. The trailing limb, it's extended in order that the leading limb touchdowns always with similar parameters as observed in label locomotion. And you can see this is label locomotion. This is the motion of the hip, the extension of the hip. You have more extension in 1 and 2.5 centimeters, but it's quite similar, and you have a very big extension. So if they need to, they can extend very well the hip joint. So it's not just the femur is just not kept parallel to the ground, as always say. And this strategy is very simple actually, and you can use it, of course, in a model in order to step up without any problem, so without any new control. So let me go now to the Japanese macaques. So Japanese macaques are, of course, quadrupedal animals, but they are trained since about 700 years in Japan for to make bipedal locomotion in circus. So you can understand, you can study how change, how adapt anatomy, but also how that control from very fast from quadrupedal to bipedal locomotion. In the pioneer works, they say that Japanese macaques walk, but we were not sure of the work, and we were interested in how they control the trunk as well when they are able to walk bipedally. So we make similar studies thanks with Professor Naomichi Ogihara in Japan and Reinhard Blickern. And we get, of course, ground reaction forces and again kinematics using Quails system. And what we get is what we got is that they use for the trunk control, they use BPP control. You see the ground reaction forces cross in a point which is this plus sign above the center of mass. And if you look to the leg control, they also have a function similar to the birds. They are also what we call so integrate. They work on the tools, and so that means they have a very long leg and a touchdown and a short leg at 2 off. So they are also absorbing energy actually. And of course, we put this data in our model that we use for the birds, and we try to find stable gates on trunk inclination between 2 and 50 degrees, and we didn't find any stable solution. But if you look to a Japanese macaque moving on a treadmill, they hardly can keep the speed. So they are very unsteady. So something is there. But interesting, if you use a very vertical trunk and more symmetrical spring-like legs, the model with the parameters of the macaques find stable solutions. So they could walk actually stable. But they don't walk. They don't use walking gaits. They use grounded running, they use skipping gaits, and they use running with aerial phases. What before was described as walking is because if you measure the duty factor, of course you have duty factor above 0.5, so you have double support phases. But actually, if you look to the congruity, which show, yes, congruity between the potential and the kinetic energy, showing that they are more or less in phase by higher than 0.5, you see that this is a running mechanic. So they cannot walk. And they cannot walk because the hip joint is still very quadrupedal-like. So they cannot extend the leg in order to have a more symmetrical functions. And okay, what we can say about the relationship between the trunk position and stable gaits? In order to do this, we make the model dimensionless, and we analyze the model with vertical trunk, and we simulate and search for solutions with different trunk angles from 0 to 90 degrees and to 180 degrees. And what we found is that after 90 degrees, you have a long or the very big fields of stability of different gaits, running, grounded running, walking. And for example, if you put the Marasuchus, which is a dino form, so this may be the first bipeds that we know. It's about 240 millions of years ago, lived in Argentina. And these guys, if you put the parameters, so the position of the center of mass related to the leg length and the trunk angle, so you see they are able in this point together with the birds, and that means that they was able to use grounded running. So that actually grounded running is this may be an ancestral gait, and maybe that evolved about 200 millions of years ago with these Marasuchus. If you go to the Japanese macaque, in all this area until vertical trunk, there is no solution, no stable solution. And there is just a line of stable solution where we are, in which you can find walking and running, but not grounded running. And but in that case, these solutions are just partially stable, while these solutions are completely stable. So that's why I say birds in 240 millions of years of evolution never change the position of the trunk to vertical like we have. So let's move to quadrupedal locomotion. So this is from Martin Fisher. So thanks Martin Fisher, we know that that the forelimbs, yes, the motion of the forelimbs are based on the motion of the scapula. So this is not the main fulcrum, shoulders, but the scapula. And we also know that the first and the third element on the front limbs and the hind limbs, when they step on the ground, they move parallel. So what Vite called Pantograph Mechanism is a parallel kinematics what they have. And today I will focus more on this forelimbs because I think it's a very interesting thing. So this limb don't have any rigid contact or the joint with the trunk. It's just the joint is made by muscular work. Yes. And why we are interested in dogs, of course, it's similar to the birds. So you have in one species 400 birds, so you can again analyze what is the influence of size, shape, behavior on locomotion. And of course, we were interested again in global dynamics, so how the motions should be the motion of the center of mass in order to have stability. But we thought all these different breeds must have the same global dynamics, but due to the fact that they have different postures, they have different mass, maybe they have different joint dynamics. And I was introducing one aspect of the forelimb, and we will discuss these 2 points. So basically, the first one is this muscle, which is the latissimus dorsi, which is a very, very strong retractor muscle. And the second muscle is this one. This is the trapezius cervicalis. And let's go to the latissimus dorsi. Latissimus dorsi is a very strong retractor, but if you look to the EMG data from dogs during the stand phase, it's not used. It's completely silent. So in this, so you see it is wide, which is, means in this graph that is completely silent. So why they don't use this retractor muscle to retract the leg? Okay, in order to understand dog dynamics, we use 4 different breeds. We use the beagle, which is a normal dog used in veterinary science. We use the whippet, which is a dog built for speed. We use the French bulldog, which is built for strength, and also the Belgian Shepherd, which is a Malinois, which is that's what we think is more closely related to what we think is a dog should look like. And of course, again, single ground reaction forces and kinematic analysis 3D, not only with markers, but also we use X-ray fluoroscopy in order to have scientific rotoscoping. And let me start with more simple models. So we're not the first to use the simplest model. So in which we do actually reduce the head, the trunk, and the tail to one segment, and the segmental legs to effective legs again. And if you have this effective leg, you have again, so like an axial, you need an axial function, which is a force, which, yes, depending on the leg length. And you need a torque to control the locomotion in the trunk. And interestingly, there is a lot of models from the simple model, but they use a spring or spring damping system. But actually, no one's take a look how the function look like in dogs, which is how this actual function looks in dogs. And they also, no one's take a look how this tangential function also looks in dogs, because we were interested in have some yes, bio inspired control strategy. So we did it for all these guys. You see the colors for each guy, and in the hind limbs you see that start here. So compression, the leg is compressed and then extended. But what happened? At the end, the leg is more extended than a touchdown. So you have energy input actually, which is the contrary to have the birds. If you look to tangential function, to torque on the hip, you have positive extension at least to the middle stand phase and then flexion. But it's basically more input energy. If you take a look to the forelimb, you have again the leg is extending, so you have positive energy system. So until that point or until this point, the dog should always become faster and faster. So where they take energy out in order to have steady state. So surprisingly, at least for me, was that they take the energy out in the tangential function of the forelimbs. So why they put energy actually and take out tangentially or rotationally is I think it's a great question. But this negative function, so this torque that actually trying to protract the leg, that in base of retracting the leg, what we are expecting for, explain why this latissimus dorsal is not active. And actually, you see they're active, so the protractor muscles, yes, in the forelimbs. I don't know how you control your robots, but I think the don't see information. So, and the second question was how they control the torque. Do they have PPP control like we observe in birds, like we observe in Japanese macaques? So we knew from the beginning that they will not use just one BPP because that will be very costly for the locomotion. So we searched for two BPPs actually, and we found they have two BPPs which are related not to the center of mass like in the case of the birds, are related to the most proximal joints. So you see the ground reaction forces crossing a point above the joints. And this is not only true for the Spiegel, it's true for all the breeds we analyze. In red, you see that it's the front forelimbs, and in blue, these are the highlimbs. You see that's, of course, that. And if you extend a simple model of the birds to forelimbs and two BPPs, you can obtain also stable locomotion using this very simple principle. So actually, we see that in the case of the global dynamics, we see that they are very similar, all these different breeds. The question is what this change bring to the joint dynamics, how they have to control the joint dynamics. And if you take a look now to the kinematics, comparing the whippet and the bulldog, these are based on scientific rotoscoping. You see that the whippet is a very parasagittal motion, and the bulldog, they have abduction about 40 degrees during stance and external rotation of the femur also about 40 degrees. So guess what? Dog have more problems on the knee, called the bulldogs. So, and going to the more yes, bed science right ways, or you see that very good indicator for disease of the joints are the joint stress. And in order to have joint stress, you need segmental forces, so from inverse dynamics, but you need also muscle forces. So in order to be able to modulate that, we produce this three-dimensional musculoskeletal dog model with 84 degrees of freedoms and 134 muscles, which is now published in scientific reports, and is the model is free for download. You can use it. And if we take a look to the forelimbs using this model, so you can get inverse dynamic, you can get also like extended inverse dynamics, so muscle activation, the muscle in this animation active when they're red. And two things that we have to look on this animation. It's one is that you see that during retraction, the latissimus dorsi, that muscle is not active. But in order to have this activation, which is similar to what we observed in dogs, you need to open translational degrees of freedom in the scapula. So if you have only rotational degrees of freedom in the scapula, during the stand phase, you will have activation of the latissimus dorsi. And we will back to the other muscles when first we will see the rats. So finally, I will go to the rat locomotion. And yes, about 5-6 years ago, we started with Roger Quinn and Alexander Hunt a project in which we tried to analyze how rats cope with perturbations. And this data should go to neuromechanical models in order to better understand the neuromechanics of underlying animal locomotion. And we designed a complex experiment with rats in which we have a camouflaged drop with the rat. And in the camouflage drop, we have, of course, a force plate afterwards. Before we use X-ray fluoroscopy, we use videos, and we implanted not only EMG electrodes in order to have the activations of the muscles, but also we implanted, maybe you can see here, we implanted some very small tantalum beads in the bones in order to have 3D kinematics, or Earthworm 3D kinematics. So we have a very big picture of what happened when these rats are negotiating with drug perturbations. And we hope to have some papers by the end of the year. But I want to show you one Emg data from that study. And so in that part is, let's say, the step before, and in this black line here is the moment at which the rats touch the paper, and this is the touchdown in the in the perturbation. If you take a look, touchdown before and touchdown afterwards, you see that comparing the muscles that we have here, trapezius, pectoralis, biceps, and triceps, you have an increase of the activation of the muscles, and you have they start activating before touchdown. So after they cross this paper, they send signals to activate the muscle actually. And you see this one, this is the pectoralis. The pectoralis is stabilizing the shoulder muscle, the shoulder joint. And maybe this rat, we don't have everything for every rat. This signals. Maybe this rats knew, or they feel that something is wrong, or there's something new coming. So they may be stiff. Was increasing the stiffness of these joints. And one point interesting is the trapezius. I come to the trapezius one. Trapezius is this violet, and you see it's active on the stand phase, and is also active on the swing phase. So this muscle first in the stand phase keep the scapula from be moving, translated to the back, and in the swing phase is protracting the scapula. And these behaviors keep in the hole. And let me go back to the model. So you see, we see this muscle. This muscle is around here. And let's start simulation. So you see the leg of the dog is not only rotating, but in the late stance, translate to the back. In the late stance, you see that the action or the activation of the trapezius decrease. So they permit the leg to move, to translate to the back. And I think this is in order that this pantograph, this parallel mechanism, it's keep in order that you just rotate the scapula and the other joints are kept fixed in order to reduce joint work. So let me summarize that. So if you are a bird, you use BPP control in order to have trunk and whole locomotion, stable whole locomotion. In the effective leg, you absorb energy actually and produce energy tangentially. You need to do that all the time in order to keep trunk, which is chronograph. And in order to reduce energy consumption, you use minimization of joint work. And in that case, if you minimize the work, you have two possibilities. even you keep fixed your segment in order to reduce your work, or you use elastic recovery. If you have joints which are have more lever arm related to the gravitational force, like for example the hip, which is keep fixed most of the time, or the intertarsal joint, which use elastic recovery. And if you have a shorter lever arm, you can move because you have a very you have less moment on that joint. And this is the case of the knee, and that's why the knee is the main retractor of the leg. In the case of the macaques, they also use BPP, which is COM based, so they are fixed on COM, the frame. They also absorb energy like birds, and produce energy tangentially. But how they minimize sum of joint work, I don't know. But I think they do that. What about quadrupeds, especially for the forelimbs? Quadrupeds, they have two BPPs, not just one, and they are related to the proximal joints. And the effective leg works completely different. So actually, opposite to the effective leg on the birds. So they produce energy actually, and they absorb energy tangentially. And this absorption, the energy tangentially, is based on this BPP control actually, but because the forces are sent to that BPP point, and that BPP point is positioned in order that to the scapular joint you have a minimal lever arm, so you minimize the joint work in that case, and you use this parallel mechanism in order to not change the joint angle, so to reduce again the sum of the joint work. And the translation of the scapula help to keep this pantograph mechanism for more time during scan. So the last thing I want to show you is what the experiments we are planning for now for this winter, in which we will have for first time active perturbations during quiet stains on the rat and also during locomotion. So we built a checking board which will be able to move fore aft and vertically 1 centimeter 10 times a second, so 10 hertz. So we have very, very powerful linear models, and this will be able also to keep. And we will combine that with measuring of ground-reaction forces with X-ray and Emg data, the rats, and we hope to have great data to share with our partners on Neuronext. We are very happy to be part of Neuronext, and that is all what I have today. And thank you very much for your attention.
Excellent. Thank you, Emmanuel. It was wonderful. I feel like I learn something new every time you talk, despite all these years. So I think we've got one question in the chat. For other questions, please drop things in the Discord so that we can have more of a record of them, and that and conversations can kind of continue offline. So you can feel free to jump between the different workshops and kind of see what's going on over with the soft robotics as well.
Okay. So should I answer the question on the chat?
Yeah.
So the question said, do you expect that the distal joint function will turn into actuation if challenging them with 5 centimeters high? I think it's about the birds. Yes. If you are talking about the trailing limb, yes, the trailing limb is actually extending also. So they not just extend the hip, they also extend the knee, they extend the intertarsal joint and also the tarsal metatarsophalangeal joint. They extend all what they have. And most interesting of that, if when they extend the leg, the control of the leg change to a similar contour that we use with our extended legs. And it means that this minimization of joint work adapt with the position of the leg, also with the how the leg is used actually. I don't know if this is the answer you're waiting for, but yeah.
All right, thank you. So
thank you all.
Yeah, we got started a little bit late. So in the interest of time, we'll kind of move on to our next speaker. So we have Kodai Kidono. Yeah, and so pull up my notes. So Kodai is from the Kyoto Institute of Technology. He's working with Hiroshi Kimura, and he has done, he has an interesting talk about split belt locomotion and gate control. And yes, excited to see your talk.
Thank you. Can you see the presentation?
Yes.
Yes.
Thank you. Okay. Good morning or hello or good evening, everyone. In Japan, good evening. Yes. So I'd like to talk to you about the evaluation of cat adaptation using a quadruple robot. So let's start. At first, we define some terms about the disabled cats. The disabled cat is, as I was said, disconnected from the upper central nervous, such as cerebellum. In the study, we define and use the different terms by where it is disconnected. For example, we define the disabled cat with remaining subthalamic locomotor region as a thalamic cat. A thalamic cat can walk spontaneously because of remaining SLR. Also, we define the disabled cat not remaining SLR as a midbrain cat. On the other hand, a cat with the upper central nervous disconnected, including the cerebellum and brainstem, we call it the cat spinal cat. Briefly, in the central nervous systems, a thalamic cat and midbrain cat remain cerebellum and spinal cord, but a spinal cat remains only spinal cord. So using these terms, let's talk about the introduction. It is well known that a cat can adapt on split belt treadmill. This figure shows a split belt treadmill experimentation Yanagihara conducted. At first, a thalamic cat walked on a tied belt treadmill. Then, lesson 4, LF belts change faster. Even on this split belt treadmill, a thalamic cat can adapt on split belt treadmill. However, this adaptation mechanism has not clarified. So let's see the detailed adaptation. But before, we define some gate diagram terms. A slow leg and fast leg means the leg on the slow belt and fast belt. In this figure, RF is a slow leg and LF is a fast leg. Then, when both legs were in stance phase, it's called bi-support phase. As you can see the figure, bi-support phase has two types. The duration from touchdown of slow leg to restore fast leg, we call B1. And the duration from touchdown of fast leg to restore slow leg, we call B2. Next, we call center of stance phase COST. It's a white circle. And we call center of single support phase COSS. It's a filled circle. The COSS is equal to the center of contralateral swing phase. So when we calculate slow leg COSS, we see the swing phase of fast leg. Center of fast leg swing phase is equal to the COSS of slow leg. And finally, we call difference between COST and COSS DBCC. Using these terms, let's talk about the detailed adaptation. This figure shows gait diagrams of ceramic cats. Let's compare the two figures above. When the belt condition changed from tied to split, we find that by support phase B1 duration decreases and DBCC generates. In this study, we call this adaptation early adaptation. And this early adaptation appears to be induced at the spinal cord. Then let's compare two figures below. During split belt locomotion, by support phase B1 increases and DBCC decreases. Also, posture stability increases so that a ceramic cat can adapt on split belt treadmill. In this study, we call this adaptation rate of adaptation. And in this study, we focus on early adaptation and try to understand this early adaptation mechanism constructively. Then we consider the problem in early adaptation from physical viewpoint. Next, we explain the other experiments. This figure shows the hind limb split belt locomotion of spinal cat freegon conducted. And this is the result. Top is tied and left is split. Comparing two figures, we find that B1 decreases and DBCC generates. So this B1 DBCC change like early adaptation in ceramic cats. Therefore, we propose the constructive model based on this experiment to understand the early adaptation mechanism constructively. The purpose of this study is to understand the early adaptation mechanism constructively. Then we consider the posture stability in the early adaptation from a physical viewpoint. To achieve this purpose, at first, we propose a spinal cat model referred to freegon experiments using a quadruped robot. Then we conduct hind limb locomotion experiments, evaluate the proposed model, and finally discuss the results comparing the gait of cats and model. Then let's talk the proposed model. We propose a spinal cat model. This model is based on a quadruped robot Kotetsu and leg controller. In previous model released in 2020, we integrate the freegon spinal cord model into leg controller. However, the gait obtained in the experiment using this previous model was not similar to that of cats. So in the study, we also integrate the stretch responses to previous model. Then we talk the details of modeling of spinal function. This is a leg controller. This controller has been developed in our laboratory. And this controller base is based on a CPG paradigm. It has two leg phases, swing phase and stance phase. And it's determined transition by leg loading. For example, when leg loading increases and becomes greater than the threshold kite touchdown, leg phase transitions from swing to stance. Also, leg loading decreases and becomes smaller than the threshold kite lift off. Leg phase transitions from stance to swing. This is a leg controller. Next, we explain the freegon leg phase transition model of spinal cats. This model is proposed through the spinal cat experiment. And this model is based on a house center hypothesis. At spinal cord, there are two types house center, extensor house center and flexor house center. These house centers excite motor neurons and determine the leg phase, stance, or swing. Also, some sensory information are leg loading, hip extension, and hip flexion sensory feedback and excite or inhibits these house centers. In addition, left and right flexor house center are mutually inhibited. In this study, we call this mechanism CIM, contralateral inhibited mechanisms. To integrate this model into the leg controller, we design the threshold kite lift off at this equation. In the equation, First term depends on x coordination of two tips. This term is equivalent to the hip extension flexion in Frigon's model. The second term depends on a contralateral leg phase. And this is equivalent to the CIM in Frigon's model. When the threshold chi liftoff is larger than the leg loading, this transition condition is satisfied. So thus, leg phase transits from stance to swing. Up to here is the previous model. In this study, we add adjustment swing duration mechanism into the previous model. When we consider the spinal adaptation, we refer to spinal reflexes. And we apply them to Frigon's leg phase transition model. So let's talk about the adjustment swing duration mechanism. First, this is a phasic stretch responses based on stretches reflex. When one leg is stretched backwards, desired phi AP increases. This phi AP is determined the swing duration phase swing duration in leg controller. That is, when a leg is stretched in stance phase, desired swing duration of the stretched leg is prolonged. And next, this is a phasic cross response based on crossed extents reflex. When one leg is stretched backwards, the contralateral phi AP, desired contralateral phi AP decreases. That is, a leg is stretched in stance phase, desired swing duration of the contralateral leg is shortened. For example, when the first leg is stretched backward because of first belt, the desired swing duration of the first leg is prolonged. Also, the desired swing duration of the slow leg is shortened by these adjustment swing duration mechanisms. Then, using this proposed model, we conducted locomotion experiments. And this is the experimental conditions. 4 belts is stop, and LH is constant speed. RH is a variable speed. So in this experiment, LH is a slow leg, and RH is a fast leg. And this is a movies. Left is a tied belts walking, and right is a split belt walking. Now let's see the result. When comparing DBCCs, we find that DBCC in split belt are larger than those in tied belts. It's similar to the earlier adaptation of Sami cat and the hind limb split locomotion of spinal cats. Then we compare the gait of cats and robots, but before we prepare indexes for comparing gaits quantitatively. When given these assumptions, we can express the gait diagonal variables using duty ratio and the period from touchdown of slow leg to touchdown of fast leg, this period. For example, a DBCC can be represented by this equation. Also, a DBCC is equal to the half of difference by support phase. And this equation fits well with the experimental data. B2 minus B1 about 2.6, half 1.63, so it's pretty near. In this study, we called these 3 parameters as dynamics parameters and used for comparing gaits quantitatively. So let's compare these dynamics parameters. Left is a spinal cat and right is a proposed model. Comparing the parameters, the change is very similar. Decrease, and decrease. So we conclude that this proposed model is valid for spinal cat from a physical viewpoint. Then we look at the detailed gait. Let's see a green area. Left is a tied and right is a split. Top is a gait diagram and bottom is a transition of leg loading, expressed by this equation. From this graph, we find that the time of COSS is black X are nearly the same as the peak time of transition of leg loading. In normal locomotion, the time of COST, because DBCC is nearly to 0, so mark is omitted. But COST at slow leg are nearly the same as the peak time of transition of leg loading. But in split locomotion, the time of COST at slow leg is a blue X, later than the peak time of transition of leg loading. So let's consider the problem. This is a normal locomotion. This is a schematic figure in normal locomotion, and this is a schematic figure in split locomotion. Time of COST is later than the peak time of leg loading. So from this figure, we consider that extra pitch joint torque increases in stance phase. So we conclude that posture stability decreased by early adaptation because of extra pitch joint torque increasing. Here is a conclusion. So if you ask, if you have some questions, please ask me. But actually, I'm not really good at listening English. So if you ask me, please speak slow or use Discord too. That's it all. Thank you.
Excellent. Thank you, Kodai. That was great. Do we have any quick questions? Okay. Yeah, so I think that was it's very interesting. And I wonder about those adaptations in relation to the VPP and how kind of that change in force profile would kind of show up on the with the VPP concept as well. Yeah, it's probably, I don't know if it's something that you've looked at the force vectors at all.
Yes.
Or just kind of the loading force. Yeah, it would be interesting to look at the force vectors and not just the normal force. So, okay. Yeah, I understand there's some language barrier here.
Thank you.
Yeah, I appreciate you taking the time and showing us your work. Thank you very much. Yeah, and we will move on to our next speaker. We have Yuki Asano from the University of Tokyo. And
okay, thank you.
Yeah, Yuki has done work with some muscle-like or muscle-actuated humanoid robots. And today he's going to be talking about kind of working towards walking with these robots.
Yeah, thank you for introduction. Can you see the slide?
Yes.
Okay. Okay, it's okay. Okay, my name is Yuki Asano from the University of Tokyo. My talk title is Trials Toward Locomotion by Human Mimetic Humanoid with Anatomically Similar Musculoskeletal Structure. Okay, let me introduce myself first. My name is Yuki Asano. I'm a project lecturer in the University of Tokyo Graduate School of Engineering. I'm from JSK Robotics Laboratory in the University of Tokyo. My research interests are humanoids, tendon-driven robots, mechanical design, human-machine cooperation system or system integration in robotics. Yeah, my main work in JSK lab is humanoids, especially tendon-driven humanoids, showing in the picture. We made a humanoid and make motions or control of this robot in the JSK lab. we made human mimetic humanoid. It means we develop humanoid robot with the knowledge of human anatomy. We design humanoid robot with human anatomy. As shown in the videos, the body is very close. It looks like human musculoskeletal structure. We pursue biofidelity human musculoskeletal structures, for example, muscle arrangement or skeletal structure or body proportions, etc. We think about a lot of things to mimic human musculoskeletal structure. By using this humanoid, research interests over human musculoskeletal structure, sensory nervous system, or brain function for motor control. We would like to investigate these mechanisms by making the robots or moving the robots, or by thinking about the humanoid. This is today's main topic, humanoid locomotion. I think there's two aspects of locomotion by humanoid. The one is leg locomotion. It is very simple and obvious. The requirements of this locomotion is modeling, balance control, or hardware capability to achieve such control. This is a common way to achieve walking by humanoid robots. On the other hand, we think about another way of locomotion. It is whole body locomotion. It means locomotion using hands or other body parts like hands or chest or legs, upper legs. The requirements of this locomotion is contact to the environment or hand capability for contact. It is important to involve this locomotion involves contact in the real world. So how treat contact is very important in addition to the left requirements. This is the actuator module we used in our human robot. Our robot is tendon-driven style, so we made tendon-driven actuators. That means wire-driven. This module composed of electrical motors, reduction gears, and wire finding mechanisms. And this mechanism includes roller cell to measure muscle tension for analyzing the behavior of the robot. And this module also includes motor driver to control this module. These components are covered by metal sheet, and the assembled style is this. Now, by using this module, we can put 400 Newton weight. It is powerful to actuate the whole body humanoid. By using the module, we assemble the module to make humanoid robot. This is the leg of the kangaroo muscle leg overview of the kangaroo's muscle. We arrange the muscle module based on human anatomy. This list is a muscle this leg has. We use 54 muscles for the leg. It means 24 muscles for each leg. This is quite large number of muscles compared to ordinary humanoid. Ordinary humanoid have mainly 6 to 7 muscles, 6 to 7 motors for one leg. From this slide, I will explain our trials to locomotion by our robot. This is the humanoid motion made from human motion capture data. This looks like very smooth and natural like human, but it is not feasible on the ground. This motion is only made in the air. So we have to experiment on the ground. This is the experiment on the ground. In this video, the humanoid is controlled by human leg motion. This person wearing a motion capture suit in his leg. The motion made from human transferred to the humanoid directly. So the robot achieves several steps made from human motion. So we confirmed in this experiment, leg power seems to be satisfied. However, it is not feasible in terms of balance control because this person supports humanoid balance to prevent falling down. So we need to implement balance control of humanoid robot. This is the examples of balance control for our robot. We implement balance control inspired by human ankle hip stepping strategy. This is very simple control. We modify ankle and hip joints according to the imbalance of displacement of COG position. Thanks to this control, the humanoid avoid falling down in spite of upper body motion. The bottom example is stepping experiment. When we push the robot slightly steps to avoid falling down. This is a similar balance strategy of human. We step when distance is relatively large. So we implement the balance control or stabilizer inspired from this human balance strategy. Yeah, this is our latest research for leg locomotion. We need to integrate the whole body motion generation and this kind of balance control to achieve leg locomotion by our humanoid. From this slide, I talk about whole body locomotion. In human, it is more natural to use the environment in locomotion. In this picture, this person holding up the pole to support his balance. The balance support by gripping the pole or pushing the wall is very natural way to keep balance in human. To achieve this, force coordination in the body or hand grasp capability is necessary. Yeah, it is very easy for human, but it is very difficult for humanoid. So there are few number of research to achieve this whole body locomotion. This is more athletic example. The climbing wall is also a whole body locomotion. This is very interesting problems in humanoids because it involves much contact to the environment. So a lot of researchers try to solve this kind of problem in humanoid robotics. But for our humanoids, human-like way is preferable. So we try to achieve this kind of whole body locomotion by our robot. This is the force control scheme used in our robot. This is the general phenomena when we contact the environment. Our robot is actuated by muscles by electrical motors. So this is elbow needs at least 2 muscles to actuate. So this is the before the contact, and this is after the contact. When we contact the wall, the one side of muscle makes high tension, and the other side slacks with low tension. So this is the problem in robotics. So we have to solve this problem by some scheme. We implement tension control to solve this problem, like shown below. The point of this scheme is we have 2 targets, the force and the length. We feedback tension and the length in this control cycle. Yeah, by doing this, we can make motion, and we can compensate the reaction force from the wall. This is the examples to confirm the effectiveness of the control. In the upper experiment, we made this kind of upper leg, open leg motion. And in this left graph, we record muscle tension during the motion. This is the length made. This is the graph made with the length control, and this is the graph made with tension control. We confirmed tension decreased when we use tension control. So we confirm the peak reduction with tension control I explained before, the previous slide. Below is the similar experiment in squatting movement. We also confirmed the peak reduction when we use tension control. And this is the example experiments to achieve whole body locomotion wall use. We try to locomotion by supporting the wall. In this experiment, the humanoid pushed the wall by its hand and steps. We confirm successfully stepped. And this is the 2-step experiment. In this experiment, humanoid stands and pushing the wall by both legs, both arms. The first, the humanoid moves slightly to move its COZ and steps fast. And next, the humanoid slightly move again to move its COZ, and then steps again. And we achieved 2 steps with this in this experiment, and we confirmed the effectiveness of the force control. This is another type of whole body locomotion. We developed hand and forearm system with tendon-driven actuation inspired from human. This is the moving example of our hand arm system. By using the hand arm system, we achieved dangling by our humanoid. In this experiment, humanoid grip the bar and lift its weight by itself, and move its leg. We confirmed the robot can dangle by gripping the bar top of the humanoid. We would like to integrate this power grip capability and locomotion to achieve whole body locomotion in the future. This is the last experiment in today's talk. This is rollover. Rollover is an interesting form of locomotion of human, especially in baby. This requires human-like smooth and round body. And in this experiment, we use humanoid teleoperation system. This person operates this small humanoid to generate motion. The motion generated by this small humanoid is transferred to this large humanoid. The reason to use this device, we don't know, or nobody knows how to make the rollover motion. We need to modify the humanoid posture interactively, real time. And by using the system, we successfully achieved the rollover by the humanoid. Yeah, this is the finish of my talk, and this is a summary. Thank you for your attention.
I have a ton, but maybe I will direct those to the Discord. Also, I just saw a presentation last week of someone who studied the kinematics of babies rolling over.
Oh, really?
So, yeah.
What's the theme of the presentation? By robot or human?
Just babies.
A baby.
Human babies.
A baby.
Yeah.
A human baby.
Yeah.
Oh, okay.
Yeah. So, and they also studied the ENGs. So, yeah, I'll try and track that down for you if you're interested. Okay. And then, yeah, I don't see any more questions. So, oh, wait. There's one from Emmanuel. What kind of optimization do you use for driving the muscles?
Oh, optimization. We do not use optimization so far to control the muscles. Or we use optimization for joint control, but this is not explained in today's talk. When we control the joint, we have to optimize the muscle tension because our robots have auto muscles to actuate one joint. It means redundant system. So we need to optimize muscle tension to actuate a joint.
Yeah.
Yeah.
Yeah. Maybe in our Discord, you can drop some links. Do you have some papers on kind of the optimization of the muscles? Yeah.
Okay.
So maybe
later I will check this code.
Yeah.
Yeah. Okay. Thank you. Thank you for questions.
Yeah, and maybe you can drop some papers in there for people to see. So yeah, in the interest of time, I think we are now running about 10 minutes behind. We will move on. And if you have more questions, you can put them in Discord and Yuki can follow up on others. So thanks again, Yuki.
Okay,
next
thank
up,
you.
We have Kitty Del Torio, who is one of my former colleagues at Case Western, and she is still at Case Western. So she got So she's the co-director of the Bio-Inspired Robotics Laboratory, and she has won an NSF Career Award, an ONR Young Investigator Award, and fellowships from NSF, NSD, or ND, SEG, AAUW, and Zonta International. She's done a lot of different studies in different types of locomotion and building robots. And today she is going to talk to us about what worms and crabs have in common.
Thanks, Alex. And it's a pleasure to be here with you all today. This is fun. So I'm going to try to, like, it's always, obviously everyone only has a short time. So we'll see if we can relate these two really different types of locomotion with all of the beautiful legged work that we've seen already this morning for me. All right, so first let's think about worms. So you can see immediately why there's a lot of interest in getting robots into very confined spaces. We have all this buried infrastructure that is super expensive to get to and then repair. And as it ages, this is becoming one of the, at least in the US, one of the top 10 engineering challenges is being able to access and repair infrastructure. And worms are doing this. We're not repairing infrastructure, but worms are accessing confined spaces without any hard parts. It's amazing. And what they're doing is we see that they're using their entire surface of their body to contact and anchor and press against the ground. And then that anchor point allows them to then slowly dig a little bit as and then they can get into these deep areas that are difficult to locomote in. So they're simple, they can go places other animals can't. We see these modular segments, and each segment can be either anchoring or moving forward. And then they can do these things like turning and undulation. And they're using their entire surface for traction. So again, I think this is really different than a lot of legged robots where that it's gonna be the foot contacting the ground. But then I was surprised and delighted to see the last talk where they're like, oh yeah, and we're going to be climbing and rolling over. So yes, earthworms are doing these things too, except it's a simpler problem because all of the segments are the same. So I think this is why they're so interesting to learn about. And how do you make an earthworm robot? So there's actually a lot of different ways. This was a figure from a review that we did in one of our papers, but now there's even more. There's a new one out that kind of pushes air out through. And so there's a lot of different ways that you can make them. These are some examples from our lab. Most of the ones from our group are made with these small little tubes that are soft, and they connect to these connectors so we can modularly swap out different stiffnesses in different places. And we have papers about what is the right stiffness for different applications. And here's a lot of this work is my graduate student, former graduate student Akil, now PhD. And we made a bunch of these different robots, and we can also simulate them. This video will play. And this is just a video of example of us assembling a single rhombus. So you might be wondering why there are these different rhombuses that make these kind of diamonds here. What is the key strategy for that? Well, we're trying to mimic what we see in the earthworm. And in the earthworm, you see these patterns of expanding and contracting segments, and then that travels down the body as the robot, or as the animal moves forward. And so what we want to get with those rhombuses is we want to get that same kind of height and length coupling. So here on the left is an example of a segment that has a large diameter and a short length horizontally. And then the same segment can then be actuated to have a small diameter and a long length. And that behavior of short, long, of the diameter and the length being coupled is similar to when in a robot segment to what we see in an earthworm segment, where there's presumably something similar to an isovolumetric relationship, where there's a constant volume of fluid inside a segment. And so then as it contracts, the fluid has to go somewhere, so it gets longer. And how do you use this? What is this for? So imagine this super simplified group of earthworm-like segments. So here's just 6 segments, And we're going to start in this position, and we're going to kind of walk through what's going to happen. So one thing you could do is, if you look at this third segment and the fourth segment, you're going to pass a wave through them. You could make that third one larger in diameter, and then you can make the fourth one longer in diameter. All right, and now your worm robot has now, the whole thing has had to translate this far. But the problem is, in order for that to work, like all of these anchoring segments would have had to slip. And so maybe they'll slip in the direction that you want, but maybe they won't. So what we're actually doing is that the expansion and contraction of the segments have to be paired. So now here's our original segment again. We're going to move that third and fourth segment, but we're going to do it together. So this one gets shorter and this one gets longer. And now the anchoring segments are staying in the same place. And as we continue, now we're at the end, and this third segment has moved from here to here. And so it has moved forward. And this fourth segment has moved from the center of the fourth segment being here to the center of the fourth segment being here. So that those segments have moved forward, while the anchoring segments have not moved at all. So this is a very simple example, but you can see that this is what we're doing with our robots. And if we don't do this, then the robot doesn't go anywhere. And it's very easy to like mess up that coordination. So what you actually want then, if you sort of expand this to more segments, however many extending segments you have between two contact points, and however many retracting segments you have between two contact points, you want them to have the same, like equal and opposite changes in length over time. So those segments need to be controlled to have this wavelength control. And then the contacting segments, they have a different state. They need to be controlled to contact the ground without slipping. So the results of this, there's several interesting results that are different from when you work on legged robots. First, you can't really plan where each segment is going to end up contacting the ground, right? A lot of times with legged motion, you can plan like where your foot is going to fall, but you can't really do that if you're not going to slip. Wherever it's already, like whatever the head is decided to do, that motion kind of propagates down, so that this fourth segment here is going to end up being, 6 widths away from the 10th segment. So it's always going to end up here. And that means we have different controllers for different states. The other interesting thing is that this is a little different from what R. McNeill Alexander thought about how peristaltic locomotion worked. He thought, oh, you have to have a different friction coefficient, and then whichever one, then you can have it move forward and not backward because the friction coefficient is different. But it's always going to be sliding along the ground like that first worst case way. But now if you don't have to slide against the ground, you can theoretically have a very low cost of transport because you're not fighting that friction. And you can move more feet at once, so you can go faster. And so you can also imagine how that would work neurobiologically is you would imagine there being asymmetric inhibition, and you can set up a competition so that each segment is sort of fighting with its neighbors to be the anchoring point. What this does is then you can adapt your anchoring strategy to a different terrain. So we have a lot of robot videos. I'll just kind of skim through some of these. So you can see we have the sensor. We have sensors, really simple sensors on each of the feet, right? In some ways, worm-like locomotion is legless, but in some ways we actually have just a lot of feet. The way we've built it here. We can do some turning. So each of these black boxes is, in the first video, each of them was one actuator, but in the turning ones, there's actually a pair of actuators, so we can actuate the left and the right different. We can measure what we're sensing, and now the robot is kind of like crawling in a really confined space. Like there's like a ceiling and a floor, but no sides, so that we can see it clearly. We can see how it's moving. Skip ahead a little bit. Okay, and we can go insert in environments that are narrowing and change motion. We can see an object ahead of us and move around it. You can still see that it's pretty soft. You can touch it and we can change how soft it is based on those little connectors that are made of tube. And you drop something on it just to prove that it's pretty robust. Yeah, so let's skip a little forward in the interest of catching us up on time, but there's still so much exciting stuff to learn from earthworms. So this is just an earthworm that we put between some batteries, and you see that it's exploring around and bending quite a lot, doing these really beautiful motions. And when we think about this, actually turning, there's a lot to learn about turning. When you move forward, there's this symmetry of your initial and your final condition are sort of mirror images of each other within a single step. And that would be true if you were doing a constant radius turn all the time. But like the point in robot steering is that you start out going straight and then you change your robot behavior so it begins a turn, right? So now that's not going to be symmetric necessarily. So every wave has to be different if you're going to avoid slip. And it has to be balanced so that the segments that are supposed to be anchoring don't slip. And so that results in these cool like wavy wiggly motions. So we have a paper on how to turn without slip. And we have a robot kind of turning without slip. And you can see that that makes the behavior more predictable. Otherwise, if you we had this case where we had one surface where we put the robot on it and have it do a turning move, and it would turn to the left. But the same motion on a different friction coefficient surface would result in the head actually moving to the right. So avoiding slip makes the robot a little bit slower, but it also makes the robot more predictable on different substrates. We've also thought about, okay, what is the optimal way of controlling? Like how many segments should be moving at once? If you look at all these worm robots, and we reviewed like 50 in this last paper that we did, like an earthworm robot looks really different than an earthworm animal. An earthworm animal typically will have a lot more segments. You can understand why that would be. But also, like an earthworm robot doesn't seem to be moving as many segments as should be possible. It should be possible to move like almost all of the segments, maybe 90% of the segments. But when you see an earthworm on the ground, it only looks like it's moving half the segments. Why is this? Is the earthworm being lazy? No, it turns out that it's actually because of the compliance and the softness of the robot, it's more work, more energy cost per distance, so higher cost of transport to move in that way. So we compared a bunch of different like speed and cost of transport trade-offs. And so that now we see, oh, look, the behavior of the earthworm can be predicted by compliant models. I'm going really fast through like just a bunch of videos. We can make the robots out of fabric. And I'm going to sort of skip over some of this. We can 3D print robots and use auxeticity, if that's a word, and non-auxeticity together to make smaller shapes and different kinds of forms. We have it even going through and narrowing. If I skip ahead, oh yeah, here we go. And you can see that like that worm-like shape actually does help it go through a narrowing, whereas without it, it can't really get through this little bottleneck feature. So this is typically about the point where people start to ask questions about setae. And yes, it's true, we have a kind of feet instead of setae, and earthworms have these setae. And some people think that they add an anisotropy in the friction, but I don't think that's true. I think what they must be doing is increasing the anchoring capability when the segments are large in diameter. And so here's my visual segue into crab robots, right? So we have earthworm setae, we have caterpillar-like legs and prolegs, where they're really like engaging with the environment. So earthworms engage with the environment all around their surface. Caterpillars are using these legs. And now let's start to think about crabs. You would not expect crabs to be able to climb trees the same way caterpillars do, but they do. And why is this? Why is this legged robot or legged animal, excuse me, so good at climbing trees? Well, I think it's because that when crabs are in surf zones, they have to be really good at grasping the ground. And so the same types of grasping that's good for climbing and that's good for, you know, anchoring to the inside of a tunnel is also going to be good for resisting wave forces. And so I don't know if you've thought about this very often, but it's kind of difficult to get to get robots in surf zones. When you are on dry sand, you want really, really low weight robots so that it doesn't sink into the sand and like not be able to get traction with the feet. But when you take that lightweight robot that's really happy on the dry sand and you put it into the waves, now the waves just knock the robot everywhere and it's no good. So you really wish that the robot was heavier right here in the water, and you wish it was lighter in the sand. Well, you can effectively do that using those things together by grabbing the sand, grabbing the rocks, grabbing the ground, increases the effective weight of the robot. And if that's possible, and this is our ONR project, then what you can do is you can imagine a robot that can use the waves and the sand and the rocks against each other. These are three typically very bad things for robots. The sand gets everywhere, the waves knock it around, and the rocks are just obstacles. But if the rocks become things that the robot can grab onto, then it can use the waves when the wave is going the direction that the robot wants to go. Then you can hold onto the ground when the wave is going backwards, and then let go when it's going the defined forward direction. So the first question is, does this even work? This all builds on sort of some climbing work that we did in the past, which I'm gonna skip over, but we use this inward gripping. And so does it work to grip the ground? And in fact, we did some testing. So here's our little waterproof robot. We'll skip ahead to where we get some waves. You can see kind of the scale of it in this video, where we can easily add waves in a tank. Now we have a bigger tank. So can they grasp the ground to exploit waves in terrain? First, dactyls do reduce the lateral travel in a wave tank, so that's good. And then if we now imagine a stance where the legs are not constant distance from each other, during stance, they move inward. And then we can measure the effective weight. And we do find that the force to lift the robot is increased if we do this attempt to grasp the ground. And this is play sand. So it's not like you would expect it to be better if it's like rocky ground and you can like really grab onto a large rock. But even for fine play sand, we can increase the effective weight of the robot by an extra third. It's true though, you're probably thinking, yeah, but what happens when you try to walk on those dactyls? So it is less good on a surface like this is the lab floor. So this is just a linoleum floor. The dactyls do decrease the speed of the robot, but not so much when you're walking on sand or rocks. So that is the quick rundown of some of the stuff that we're doing. And I think in both cases, what we see is that it's so exciting to learn from animals, to see how they're like living in these environmental niches, but not just like tolerating like, oh, there's rocks or, oh, there's these tunnels. They're really using these confined spaces, and they're using the environment in really unique ways that are different from how typically, like as a robotics engineer, we're going to design them. So just another plug for biological inspiration and how much fun it is to learn from animals. And I think here I'm at time, so I want to thank my team, and thank you all for listening.
Great talk, Katie.
Thanks, Alex.
Yeah. Do we have any questions? Always got to wait an extra 30 seconds on Zoom for questions. So yeah, I really liked how, I guess kind of following up on like those dactyls, like you said that they work just as well walking in like regular sand. And basically the only structure they didn't work on was like a super smooth one.
So by didn't work, I mean, you can still get some forward progress, but it's a lot slower, right? So like if you look at this graph here of like, so these were the original feet that were just kind of like the sort of a typical sort of end in a ball feet. And actually it was more like end in a flat circle foot. And so then when we add the dactyls, now it does go a lot slower because the dactyls are slipping more on the smooth linoleum surface. But actually then if you look at in what happens in sand or rocks, like all of the feet are slipping, you know, in more of a granular media, because the granular media kind of gets kicked back behind. I mean, this is sort of even preliminary now, because we could optimize the gait, which we're working on now for different substrates. But this is just like what happens if you have a robot that's walking perfectly fine, and now you give it terrible feet. Not terrible feet, but terrible feet for walking on smooth surfaces, unexpected.
Yeah. I was going to ask
like
if changing the gait, and how many legs do crabs have?
So crabs are decapods, so they have 10. Yeah, so it's like nominally 10.
Okay.
So we are using
But two of them
hexapods
are-
because like it's, yeah, right. And then some of their like legs are actually like graspers. So, but we are using usually, like we even have a 4-legged crab robot in our lab right now, because sometimes you make 2 legs and you want to see how they're working, or you know, you make 4 legs and you want to see how we have an 8-legged one. We're kind of changing it up. Because we want to figure out like what is the way that we can insert the dactyls like into the sand nicely to get well entrenched, so that when the wave hits it, it doesn't get moved. Oh, someone has
Yeah,
up
I
there.
think we got questions now. Nick, I think, has the first question in the chat.
All right.
Yeah, I'll ask it verbally because it's a little bit of a mess. So Katie, great talk. Every time I see the worm work, it warms my heart and soul. So I think what is brilliant is, like you said, the peristaltic motion really is pseudo-legged locomotion in a way. Can you imagine, or do you have plans to integrate a flexible body that maybe does peristalt with legs, such that you get an inchworm type motion? Or like, have you seen this beetle that has a bounding gait over sandy dunes?
Yeah, so there's like a huge variety of what insects do. That's a little different. And there's parapodia, right? Like it would be so fun to make a worm robot with, so like there's these swimming worms that have like just a lot of legs, you know, on the sides, and the legs are like swimming legs, and then they get to the ground and they're crawling. So there's a lot of really cool things that should and could be done. I think, you know, there's a lot of exciting ways to interact with the ground, and if the legs are getting in sand or waves, then like it's different, because it's like the whole surface of the leg is then like pushing and scooping the sand, and there's different gaits that people are trying with this.
Sure.
Yeah. So I think like there's a lot, but in terms of the difference between like an inchworm gait and like a peristaltic gait, is that the peristaltic gait that some of those worm models are using, is that the diameter is getting smaller instead of lifting up off the ground, which means it's really good for really tight spaces. Now, if instead of your channel being smaller than your max diameter, then you want to kind of undulate to brace against it.
Got it. Yeah, that's awesome. Thank you. Thank you for a wonderful answer to my vague questions.
Next, we got a question from Holger.
Excellent talk. I really like the earthworm. I can tell you that's really fantastic. It was a little bit of a funny question. When do you give them a brain? In any case, but altogether, all the talks, I think they showed one general principle that you can identify very easily, and that's the interaction with the physical environment. And so in all of those talks, really, what you could see that there is some sort of computation, well, morphological computation done in biological systems altogether. And that reduces the complexity of any different state changes and makes it way easier to deal with it. The other thing that I've found in all talks very interesting is it was a lot about local controllers, which biology is very great in using, because it's all a modular system in a way. You know, you have joint controllers and you couple them loosely, and then you coordinate the whole gate or whatever you want to do. That's really great. Another big principle in biology. Now the $100 million question is, how do you do something that has a purpose, right? It's not just coordinating the limbs or coordinating the legs or whatever the movement pattern, but how do you combine some sort of balance control on the one hand side with any planned or voluntary movements? And I think this is one of the bigger questions altogether. But
yeah, it's like
brilliant. Yes. Sorry.
there's like a greediness, right? Like, should the robot take the opportunities that it gets, or should it be like, no, this is what I'm doing. Forget what's happening around me. I am doing, you know. It's like an even broader question in like research too, right? Like, are we going to take opportunities? Or are we going to just like stay focused? And there's got to be times for both, right? There's got to be times when the robot like doesn't care, the things that it doesn't care about. It's going to just take whatever opportunity to like get a foothold that it can. And then, you know, there's got to be things that it matters, like maybe the motion of the head going in the right direction. And you can see with earthworms, it's pretty cool. Like, it's not just straightforward, like, okay, now I see where I'm going and I'm going to plan it, and I'm going to do it. It's like, okay, I'm going to go and then I'm going to come back. I'm going to go, come back.
All right.
Yeah, in a way they have an easy life. In a way, they can just go with their immediate opportunities, I would say.
Right? Yeah.
Okay. I think I'll answer Emmanuel's last question about worm robots controlled by things other than fluids, and lots of Katie's where robots are actually controlled by motors with kind of strings wrapped through sections. So yeah, there are different ways to do the worm robots.
And that's because it's been convenient for us. We want to have a lot of sensors and a lot of degrees of freedom. So it's convenient for us to have kind of like this kind of diameter test robots. But we have some like that are controlled by various other. We have one that was controlled with water that you might have seen, the black one with the little scales. And some people obviously do it with air, like this guy's got water inside. So there's a lot of different ways. There's no like one way. There, you know, all you need is a bunch of identical segments where you can have this like relationship between the length of it and the diameter. And you put a bunch of them together and you can make it crawl like a worm.
Right, right. Yes, because my question was about how do you get a robot that move for a long time? Because if you have just fluids, it's going to be hard to move.
Right. Yeah, you can't get them to go very far. You have always kind of tethered. So yes, yeah, we are using electric motors, and sometimes the robot could carry the battery, but then it like messes up our perfect weight distribution and it changes our analysis. So we've been keeping the power off board for a lot of them, but it wouldn't be that difficult to put it on board.
Okay.
Okay. So I'm gonna stop our kind of Zoom session now. We'll be back in 45 minutes. You absolutely feel free to continue conversations in Discord. So there are channels where you can do video and audio chat, like you could meet in the lounge, and drop questions also in kind of the workshop chat. So we'll be back in 45 minutes. Thank you, everybody.
Thanks, Alex. Thanks all.
Hey, Alex. I would share my slides, but I can't. It says,
Yeah, I think because I'm sharing this screen.
I see. Okay.
Yeah. So I can stop the share and let you take over there. Okay, so welcome back, everybody. I hope it's always hard to tell how many people are actually in the room in Zoom. So I would like to welcome you to what would maybe be considered the afternoon session, though it is still morning for myself. And we are starting off with biology again. So Cynthia Moss is professor and chair of psychological and brain sciences at Johns Hopkins University, where she directs the Comparative Neural Systems and Behavior Laboratory, aka the BAT Lab. And I'm excited to have her here today to talk to us about airflow sensors on bat wings and sensing in general. I think it is an underappreciated topic in the area of bio-inspiration and biorobotics. And without further ado, I'll let you take it away.
Well, thank you very much, Alex, for the invitation to participate in this workshop. It's really been great. I've learned a lot so far. Now, can everyone see my slides?
Yes.
Yes, okay, great. So the title of my talk, Bat Wing Airflow Sensors Support Aerial Maneuvers. Now, airflow patterns across the wings of flapping bats have been studied in several laboratories. Haydenstrom and colleagues have shown that they've measured wake structures and airflow patterns across the wing of flying bats and demonstrated complex aerodynamic wake signatures and also vortices that may contribute lift. And these studies raise the question, can bats sense airflow patterns across their wings? Now, there are over 1,400 species of bats, and all that have been studied to date show wing hairs, very tiny hairs embedded in the wing and also in the tail membrane. And here are scanning electron micrographs of such wing hairs that have been investigated in the Egyptian fruit bat, the big brown bat, the short-tailed bat, and the common vampire bat. In all these species, the hairs are tapered, similar to whiskers, and hair length correlated positively with body mass of each species, but not with the wing aspect ratio, flight speed, or diet. Now, I'll tell you a little bit about some neurophysiological and behavioral experiments on the aerial insectivore, the big brown bat, Eptescus fuscus. This species makes rapid changes in flight direction to intercept prey in open air. And a tropical fruit-eating bat, Seba's short-tailed bat, Corollia perspicillata, and this species maneuvers to find fruit in dense foliage. So here's another scanning electron micrograph of a bat wing hair. It's sort of embedded in this dome structure you see here. And the density of these hairs across the wing is rather sparse, about 1 hair per square millimeter. Length varies from 100 to 600 microns, depending on the location. The base diameter is about 3 to 4 microns. And at the tip, the diameter ranges between 300 and 800 nanometers. So these are located predominantly along the ventral and dorsal trailing edge and also the dorsal leading edge. So airflow patterns across the wing vary as the bat beats its wings and flaps its wings. And the friction of air against the wing causes the formation of a thin layer of air that moves at reduced velocity, the boundary layer. And at the peak of wing curvature, laminar flow at the boundary layer separates from the wing surface and vortices are created. So we're interested to know how the hairs on the wing may respond to changes in airflow. So we've done some neurophysiological experiments and specifically recorded from primary somatosensory cortex and stimulated the wing with air puffs. And what you see here are recordings from different regions of the primary somatosensory cortex that are responsive to different regions of the wing. And what you see here, blue, is a cortical response to air puff, shown in open, when the wing hairs are intact, stimulating this region of the wing. And when the wing hairs were removed, then the response was greatly diminished. And the same pattern appears in these other recordings. So this is a recording in primary somatosensory cortex that responded to stimulation of this wing region. So here we see a response when the wing hairs are intact, and that response is diminished when the wing hairs are removed. Similar pattern here, response to stimulation of this region of the wing, and also here, stimulation of this region of the wing. So it appears that the wing hair depilation affects the responses of cortical neurons to airflow stimulation. So the airflow sensing cortical neurons also show directional selectivity, which is illustrated here. So again, we have examples of 4 neurons that show directional selectivity and different preferred directions. So what you see here on the bat wing are results from recordings from primary somatosensory cortex with the preferred airflow direction illustrated by the arrows. And what we find is that many neurons show directional selective responses to reverse airflow, that is, airflow from the trailing edge to the leading edge of the wing. So now I'll tell you a little bit about a behavioral study that was conducted some time ago with the short-tailed fruit bat, Corolia perspicillata. So in this experiment, the bat was trained to fly through an opening in a net, make a turn, and then make another turn to fly through a second net opening to receive a food reward. And high-speed video cameras were used to track the bat's flight behavior. And these experiments were conducted with the wing hairs intact and then following depilation. And the depilation was carried out with just a commercial cream. Okay, so here we have average flight speed as a function of time from target. That is, here as the bat made the final turn to reach its food reward. And in baseline recordings shown here, we see that the average flight speed along the trajectory was lower than following wing hair depilation, shown here with these different colored plots. So first we depilated the trailing edge of the wing, then the leading edge of the wing, and then the entire wing. And you can see that the change in the flight speed was not different across these different depilation conditions, but all higher than the baseline. And then we also looked at the average turn angle. And what we see is that the bats in baseline make sharper turns, and in following the wing hair depilation, they make wider turns. So now I'm going to shift to some more recent data that we've collected, which looked at the question, the contribution of wing hairs to flight behavior and insect capture in the big brown bat, Aptesicus fuscus. And here's the basic setup. The bat was trained to take a tethered insect, which you can see in the video here, a bat flying in to take a tethered insect. It's just a mealworm hanging from a string. And we've got high-speed video cameras to record the flight behavior, and also microphones to record the echolocation behavior. Should add that in the study of the short-tailed fruit bat, Corolia, only the dorsal wing hairs were depilated. And we started here in this study with ventral wing hair depilations and then moved to dorsal. So here is the basic layout of the experiment. We first took baseline recordings of the bat's flight and echolocation behavior. Then we introduced a sham treatment. That was the animals were treated with water. The wing hairs were not removed. And then we divided our animals into different groups. One group received wing hair depilation first, another group received tail depilation first, and then subsequently the animals that received the wing hair depilation first received the tail membrane depilation, and the animals that received the tail membrane depilation first received the wing hair depilation. And finally, in 2 animals, we depilated the dorsal wing and tail membrane. So I'll just go through our results now. First, we measured the time to attempt capture, that is, intercept the insect. So we have time here on the y-axis, and then the different treatment groups: baseline, sham, tail first, wing tail, and dorsal. And what we see is that the wing first treated bats showed an increased time to capture. And when the tail first bats received wing hair depilation, they also showed an increase in time. And then the dorsal treated bats showed an even greater increase in the time to attempt capture. We looked at capture success, and here you see that the wing first treated bats showed a decrease in capture success, and the wing tail treated bats as well. And interestingly, the capture success in the dorsal treated bats returned to baseline. Now we also looked at flight speed, both the normalized velocity and then across different distance blocks relative to the target, so that's 0. And so we see here, this is the baseline shown in black, and here the wing first shown in pink. And we see similar effects on flight speed following depilation from the study of the short-tailed fruit bat. But interestingly, we also showed that there was an increase in velocity of the sham-treated bats, that is, the animals that were treated with water, but the wings were not depilated, but this the increase in flight speed was greater following the wing first and tail first and wing tail treated bats. You see here, the tail first treated bats did not differ from baseline, so that over time, this effect of the sham treatment disappeared. And interestingly, the dorsal treated bats, their flight velocity, normalized velocity, returned to baseline. We looked at wing beat frequency as well, and here we see that the tail first treated bats showed an increase in wing beat frequency, as did the wing first and wing tail, and then dorsal treated bats returned to baseline. Now, past work has shown that several different species of bats actively control and adapt the shape of their tail membrane in order to generate thrust and lift. And additionally, there's a coordination between the flapping of the wings and tail membrane, demonstrating that the wing beat cycle and movement of the tail are closely related. Interestingly, our data show an increase in the wing beat frequency even when only the ventral tail membrane is depilated, suggesting that there are interactions between the wing and tail membrane, which have been disrupted by the depilation treatment. And finally, we looked at turn rate, and here we see that there's an effect of turn rate on the sham-treated bats, a much larger change in the wing first treated bats, and also the wing tail treated bats, and also the dorsal treated bats. So these animals are making wider turns following the treatment. So just to summarize now, following the ventral wing depilation, we see that there's an increased time to attempt prey capture, decreased capture success, increased flight speed, and decreased turn rate. And following the dorsal depilation, we see that capture success, wing beat frequency, and flight speed return to baseline. So overall, these results suggest that wing hair sensors contribute to the flight kinematics and prey capture, and asymmetric wing surface depilation appears to produce overall larger effects than symmetric depilation. I want to acknowledge those who did the work that I've reported on today. The behavioral experiments with the insect eating bat. The big brown bat were carried out by Brittany Boublil. This was her dissertation research. And some of the past work I summarized, the behavioral studies with the short-tailed fruit bat were carried out by Chen Chu, Ben Falk, Wei Zhan, Jana Barcelo, and the neurophysiological recordings from the big brown bat were carried out by Mohit Chadha and Suzanne Sterbing. And we've been funded by NSF and AFOSR for this work. And I thank you for your attention.
Great, thank you. Looks like we got a question from Holger.
Thanks very much, Cynthia. That was great. I really like the work in bats a lot, in particular because these, in connection with the function. I mean, these hairs you have been looking at for a while, and the idea is that disrupting the functionality has probably some consequences for the stability or the control of the stability, I would imagine. And it's sort of implicit in the data. I'm really surprised that you find such a clear effect. Well, I'm surprised about the responses in the somatosensory cortex. So if this is a very fast reflex that's important to facilitate the maneuverability, say, I would imagine that there is a spinal reflex that is really contributing to flight stability as well. So there might be different levels. So what do you think is happening there?
Oh, so absolutely. I should say that the responses in somatosensory cortex are sort of brief, generally brief onset responses. You know, there's a change and the neuron responds. We would really like to go lower in the system, down into, but it's very, very difficult to access these spinal neurons. So we haven't done that yet. Doesn't mean we won't, but the primary somatosensory cortex is the first place to start. We've also looked at the midbrain and see responses there.
Yeah, thanks. Yeah, it's great. I mean, I can see why there is. I mean, for us, it's the same thing. So some of the spinal reflexes depend on proprioceptive feedback or whatever. And we are getting aware of that because there are projections to our somatosensory cortex as well. But at the same time, reflexes run already, similar to some reflexes that are elicited by nociceptive systems or something like that, right? Sometimes we act already, even though we haven't been aware of it.
Exactly.
So yeah, so it's really interesting. Thanks very much.
Oh, sure. Thank you.
Any more questions? I've got maybe a couple related questions of, seems like some of the effects were a little more subtle than others. And I'm wondering, is it obvious that the bats are flying differently after the depletion?
No, it's not obvious. I mean, so, you know, all of this, these insect capture trials go very quickly, and we record them on with high-speed cameras, and we do detailed quantitative analyses. And it's really only in these analyses that we find the results. You know, in our observations of the bats, just in real time, we don't notice that there's really a big change. And so, you know, they really have mechanisms so they're not completely disabled when the wing hairs are removed. But some sensory information contributes to the finely tuned behaviors.
Yeah, what sensory information kind of dominates, do you think, the flight behavior?
I'm sorry, what kind of sensor? I mean, like the airflow sensing versus
like muscle sensing?
Yeah, and proprioception. I mean, I think they all work together, and we haven't at this point been able to parse that out. And of course, the bat has echolocation behavior as well, and I didn't have time to go into it, but we do see some effects on the echolocation behavior in these wing hair depilation experiments, and specifically when the bat prepares to take an insect, it produces a very rapid sequence of echolocation calls referred to as the terminal buzz. This is the terminal for the insect if the bat is successful. Okay. And we see that the duration of this terminal buzz is shortened in the wing hair depilated bats, which suggests that the bat is having some difficulty coordinating its sort of preparation to take the insect. Perhaps it's sensing that it's flying at a different speed than it actually is, although it also has echo arrival time information to tell it how far away it is from the target. But it is relying on multi-sensory information.
Interesting. Katie, did you have a
Yeah, great talk. Thanks so much. Like, is it possible to amplify the hairs? Like, what if you use like eyelash extending products, or like you added some tiny, I don't know, like, can you make them, I guess, be opposite as when you remove them, or?
Yeah, that would be tricky. I mean, as I mentioned, they're extremely very short, and I don't know if we could modify the length of the hairs. I'm not sure it would necessarily amplify their effects. It might still change the effects because the activation of the receptors could be modified by that increased length.
Okay.
But interesting idea.
Can I ask another question as an engineer now? Do lots of flying animals have this ability to sense the surface? Like, I would imagine feathers would work similarly, but like on a fly or a flying insect, do they have these sensors?
Yes, they're insects, birds. I mean, they have hair-like structures, feathers that do respond to airflow.
Yeah,
And
they
they
also
use
have
them
some
for different ways.
strain. Sorry.
Yeah. Go on, Holger.
Yeah, well, so they have some campaniform ancilla which can measure some strain as well, which would be could be related to airflow as well, and disruptions of airflow specifically.
Yeah. And the bat wing membrane is highly specialized. It contains, of course, these hairs I've described, but also stretch receptors. There are muscles embedded in the wing to change the camber that affect the sensing. It's a really rich area for research, and we don't know that much at this point, but how all that sensory information is put together.
Thank you.
Well, thank you again, Cindy. If you have more questions for her, let's drop them in the Discord. And we will, you might have a chance also during our discussion period to bring up more things. So let's move on to more now the engineering side of recreating that flight. So we have Alireza Ramazzini from Northeastern University, and he he's going to talk to us about his framework, morphing via integrated mechanical intelligence and control, and building micro air vehicles and a bat robot for flight. So welcome, Alireza.
Thank you very much. Thanks for inviting me to this workshop. I just share my slides now. Hopefully you can see my slides.
Yes.
Okay, great. So, thanks for inviting me to this workshop. My name is Alireza Ramazzani, and in this talk, I want to give you a very brief overview about ongoing research in my team on sort of creating MAVs that have some of the morphing capabilities of bats. As you know, these are high dimensional systems. It's not really trivial to integrate all of these active and passive coordinates within an MAV design with prohibitive design restrictions, mainly payload, for example. So let me start with a very brief motivation, and I'll go to some sort of mathematical framework of why we look into integrated mechanical intelligence and control, and give you some update on some of our results. So success of biological systems, as you know, can be defined based on how with minimum structural materials they can make maximum effect on their environments. And maximizing effects per unit of energy expenditure leaves more energy for more vital tasks. With body morphing capabilities and deployable structures, etc., the systems can achieve these objectives, which are key to their survivability in their habitats. And among these animals, vertebrate flyers are probably unique in their morphing characteristics because they can do dynamic morphing within their gait cycles. For example, unlike a jellyfish where its passive dynamics dominate body conformations, birds can actively change their body configuration through the synchronous and active movements of many joints. And the passive dynamics essentially is partly involved throughout this body reconfiguration process. Bats push the limits of active morphing among vertebrate flyers. They push it to the next level. This is a bat perturbed by a powerful ergot. In addition to the cyclic wing expansion and contractions you see, which involves the synchronous movements of like over 40 degrees of freedom in some species, it can be seen that the animal regulates these kinematic modes actively to stabilize its flight dynamics. So the million-dollar question is how they can activate so many joints synchronously with the limitations enforced by their body size. And from an engineering standpoint and from a robot designer standpoint, how can we copy this flight apparatus? Challenges of the robotic biomimicry of this morphing system encompasses like modeling fluid structure interactions, high-dimensional locomotion control, and robot design. My research goal, and my team's research goal, is to find actuation architectures that make dynamic morphing possible in a small, self-contained microaerial vehicles inspired by these creatures. We call these MAVs, just for short, morphing MAVs. So the approach that we have been trying to adopt here is based on designing and augmenting computational structures with feedback and readout. Simply speaking, the design philosophy here is that the robot morphology must contribute to the dynamic morphing process. Otherwise, you won't be able to deal with the very limited payload budget that you have in the system. Embodiment concept, as is also known in the community with various names, mechanical intelligence, computational morphologist, etc., has been recognized in various disciplines, science, engineering. Perhaps the most famous locomotion-related examples go back to passive walkers, tensegrity systems, many other examples. So it's not a really new concept. However, its application in the design of winged systems has been overlooked. It can offer solutions to questions such as moving mini joints, dealing with curse of dimensionality, as I'm going to later talk about it, deal with tracking challenges, and also can help us from engineering standpoint answer questions to underlying mechanisms of energy efficiency in vertebrate flyers. Energetic efficiency of locomotion has been extensively studied in legged systems, but we don't have that those results when it comes to flapping wing community. So let's briefly take a look at how winged systems or flapping wing systems have been treated so far in this community, and how we are doing that differently at NU. Flapping wing works mainly dominated by insect-style designs, as you may know. In most of these cases, insect models are utilized to even like larger flapping systems, which is known that insect propulsion is not really scalable, but despite that, this has already been used in larger flapping systems. Insects are monomodal systems. This means the only dominant kinematic mode in their flight is a plunge or flapping motion. Three important properties of insects include massless wings, fast flapping dynamics, and active wing morphing, no active wing morphing capabilities, mainly passively. As a result, simple models such as averaged models here can be applied to describe their flight dynamics. In general, these are elegant robot design and control problems, putting aside like size related issues and challenges associated with that. They have simple mechanisms in general. Their control design is relatively straightforward because insects, from control design standpoint, are parachute stable, meaning the CGs are beneath the center of pressure, which is basically make this like a pendulum and it's a statically stable configuration. In contrary, morphing MAVs can violate all of these insect style sort of properties and therefore yield completely different flight mechanics, which so far has been only studied in simulation or through like attaching sensors to birds and bats. This is our latest morphing MAV that we have been able to successfully test in my lab at NU. This model possesses 4 modes, 2 per each wings, and the robot has 22 degrees of freedom in its wings. It weighs about 40 grams with its onboard electronics and a battery. It can carry a small camera, and the wingspan is less than 1 foot, actually. And I have to mention that the vehicle has been stabilized with the help of a tail here on the right-hand side of the screen. At this point, we have not been able to stabilize this with closed-loop feedback. Here, wing width frequency is not high enough compared to the natural frequency of the motion to apply sort of quasi-static approaches, and the wings are sort of massed and each constitute about 30% of the total weight. So let's take a look at the governing equations of motion for these morphing MAVs. We will use this model to sort of introduce a twofold tracking challenge in morphing wing flight. And then we will show how a full closed loop feedback solution towards this tracking problem can motivate an integrated computational structure and feedback framework. So if we consider the sort of wing joint torques as the inputs to the system, it is straightforward to show these models have the following affine and control forms. These are sort of models that are less common to be seen in flapping wing community. We used to see non-affine in control forms. The joint actions steer inertial dynamics contributions as well as aerodynamics contributions. The advantage of a model like this is that it nicely describes why at like near or post-stall conditions, when aerodynamic forces vanish, I mean, here it's denoted by U2, these systems remain controllable, or why the systems theoretically can perform zero or non-zero angular momentum turns, such as their biological counterparts, because they can use their IDCs. The major disadvantage here is that a model like this is not really offering a practical solution to robot actuation and control design, because essentially torque control is not possible here. To the best of my knowledge, torque control at larger robots, robot manipulators, Lego systems involved extra power electronics, extra sensors, extra computing resources, and we simply don't have these resources on these MAV. So one of our most important objectives is to find a replace to these joint actions that can deliver the responsibilities of these joint actions. So let me just briefly go through some of these responsibilities. And the first responsibility here is to generate kinematic modes in the system. And mathematically, that can be achieved by enforcing these time-dependent, for example, constraints, which make Veen coordinates slave to predefined time-dependent vectors. The second responsibility is to regulate these kinematic modes for force tracking purpose. And this is what I call a twofold tracking problem. Sacrificing of joint trajectory tracking versus force tracking or vice versa here is not possible because each comes with their own importance. Dynamic morphing is key to energetic efficiency of flight. I'm going to briefly talk about it in a few minutes. And you certainly don't want to miss that. Also, force tracking is important from a flight control standpoint. There are various ways to look at this a twofold tracking problem, which in my opinion is not a trivial sort of closed loop feedback design problem. We take a sort of a reference governor based approach to solve this problem in a decoupled fashion, which motivates the integration of mechanical intelligence and control. So let's first use our joint actions to achieve a pre-stabilized model that guarantee the realization of a stable kinematic modes in the system. The mechanical version of this pre-stabilized model is a system with computational structures. It is possible to theoretically prove this, but I'm going to skip this for the sake of time. For force tracking, the pre-stabilized dynamics or the system with computational structures can be augmented with a new input. In control community, this is called a primer. Later, I'm going to call it a regulator. It helps to modify the response of my closed loop system for the sake of force tracking. This has a very interesting geometric interpretation. And, let's consider the status space of my pre-stabilized system or system with computational structures. The locus of all the steady state solutions of my pre-stabilized dynamics is a line that goes through the origin. Any point on this line describes a gate for my morphing MAV. And the primer's responsibility here as a new input to the pre-stabilized system is to push these gates across this line or change the gates in my morphing MAV. Then force regulation here can take place as if you are doing like motion planning in the status space of my pre-stabilized system. So the major drawback of this decoupled view is that it does not give you precise force tracking. The advantage, however, is that it gives you, with some trade-offs, joint tracking as well as force tracking. But the big impact of this simple derivation from a robot designer standpoint is that new inputs with desired properties. Later, I will briefly explain what are these desired properties can be introduced through the design of A and B matrices to essentially solve the curse of dimensionality and the twofold tracking problem. As it was briefly mentioned earlier, A matrix here captures the behavior of my computational structure, and B describes how the new inputs are integrated within the computational structure. Both can be systematically designed to address the challenges that we are facing here. So to design these A and B units through the design of the computational structure, we have defined a problem called partitioned actuation architecture problem. Here, the idea is to find new inputs composed of mode regulators and mode generators. Essentially, mode regulators are small and low power actuators that in order to be able to regulate the kinematic modes, their effect must be emboldened through the design of the computational structure. And mode generators are powerful actuators, usually electromechanical, that drive the kinematic modes in the computational structures. Since they are bulky, their number must be minimized. As a result, the goal here is to design a computational structure with minimum number of mode generators that can demonstrate maximum dimensional complexity of the system. We define this problem as a topology optimization problem. Tools that we have used so far include solid isotropic microstructure penalization, known as SIMP, or evolutionary structural optimization. But a little bit about the hardware aspects of our framework. So the motivation behind some of the kinematic modes that we have taken so far, we have considered plunge motion, flexion, extension within the arm wings. So there's a motivation behind these kinematic modes. And the motivation here is to capture a threefold energy efficiency mechanism from bats. The first mechanism is based on maximizing net positive aerodynamic forces by collapsing the arm during the upstroke, which reduces the negative aerodynamic forces. And the second mechanism involves minimizing the upstroke time by collapsing the wings during upstroke, as the collapsed wings travel faster in space due to the reduced moment of inertia. And third mechanism is based on absorbing and releasing elastic energy during the downstroke and upstroke to facilitate the unfurling of the wing at the end of the upstroke. The fabrication methods that we have used to create these computational structures based on PolyJet 3D printing, which allows incorporating rigid and compliant components within a single design, almost in a compact form. However, in the past, we have faced challenges associated with physical realizability of these topology optimization results, as these are components that go under fast flapping motions. We have also integrated hyperelastic models within the topology optimization to kind of make simulation-informed decisions to increase our chance of success. Here you see an example of a computational structure in action. One of my students drives the response of the structure. The student's fingers here at the base of the structure sort of emulates the responsibilities of a mode generator. A little bit about the type of regulators that we use. Our mode regulator candidates that we have considered include shape memory alloy based and piezoelectric actuators. These actuators are light and can be integrated within the computational structures in several numbers. However, more important than the hardware itself is their location within the structure, which is very important. Because as I said earlier, these have very limited output performance, and they must synergistically work with the computational structures for kinematic mode regulation. Here you see an example of optimal locations for our SMA-based actuators. They are placed in such a way that the kinematic modes are affected, our desired kinematic modes are actually affected the most. In conclusion, our main motivations to design morphing MAVs is to achieve agile and efficient aerial robot designs. The major challenge here is that our state-of-the-art actuators cannot match the energy density of mussels and vertebrate flyers, which are known for their dynamic morphing capabilities. And the solution that we're proposing here is based on is based on integrating mechanical intelligence and feedback, which has already been experimentally validated, but it's ongoing research. We still need to add more design considerations to the current framework. With this, I want to close my talk. I'm thankful to to the organizers of this interesting workshop, and thanks to you for attending this workshop. Thank you.
Great, thank you, Ali Reza. Do we have questions? Holger.
Yeah, that's really excellent. Thanks very much. That was quite amazing. I guess at some point you will have to think about a C matrix. Is that right? So you want to control what is happening with your device and how you sense the modes you want to control.
Yes, and that's actually the stage we are sort of trying to. So we have sort of methods that allow us to predict complex fluid structure interactions within a very short time period. Of course, we cannot, predict these complex behaviors. Let's say we cannot find a function that globally can predict these behaviors. So therefore, we are sort of limited to short-term predictions of these behaviors. And the next step, what we are considering is to regulate these network of regulators within the robot to actually control its flight dynamics. One thing we have noticed, and this is, I think it's quite unique to tailless flapping flight. They are notoriously unstable, longitudinally unstable. And we had to attach a very long tail to the platform to stabilize its flight dynamics. So the very first step for us would be to use these regulators to stabilize the longitudinal dynamics, and then we would like to see if we can do hovering, because in terms of efficiency and propulsion efficiency, we are doing a very good job. We will be able to do some hovering, but as I said, stabilization might be a challenge at this point.
Yeah, passive stabilization is a very good trick. In the really maneuverable flies, like compact flies, which do not have a lot of passive stabilization, if you remove their gyroscopic sense organs, the halteres, they will crash right away because they can't deal with high angular rate disturbances anymore. But if you attach a thread to the abdomen, they can fly again, simply because that high dynamic range perturbations are passively stabilized. But it's really the other thing that appears to be the case is that the sensors providing information about optic flow, say, use the same coordinate system that you would use to describe the modes of motion during flight in these animals. And that is computationally extremely efficient. Okay. But anyway, this is, I didn't know that you can do things like those you just described. It's amazing. Thank you.
Thanks.
Excellent. We also have one question in the chat, and then we'll move on to the next speaker. So from Nick, the joint mechanisms are really interesting with kind of that 3D printing. Are there any concerns about fatigue over time? How many cycles can they withstand before breaking?
Yeah, that's a very, very good question. And they can fail after going through a certain number of cycles. And we have been exploring a range of materials to find the best solution for what we are looking at. But that's one of the challenges, I would say, on the hardware design side of the problem. That these joints eventually, they don't have that resiliency that you would see on a real animal, obviously. So yeah, that's a big problem at this point for us.
More challenges in manufacturing. Okay.
Yeah.
Thank you again.
Thank you.
And for our last speaker, we have Singbai Kim from the Massachusetts Institute of Technology, and excited to see and learn about his latest work.
Hi, everyone. I will just share the screen, share my slide. So if I can successfully do that. Do you see the full screen? Okay.
Yes.
Hi, my name is Sang-Bae Kim. Thanks for inviting me. This is my first time, so I wasn't quite sure what content is right proper, but I will just briefly introduce what we've been working on at MIT. So title is Robotic with the Physical Intelligence is sort of like the goal of my mind and our lab's vision eventually. And the physical intelligence is such a weird, vague word, and there are many people use different definition. I hope I can explain that in my talk. You know, everybody probably, many of you already seen DARPA Robotics Challenge result, and these are somewhat exciting part of the video. Many of you have seen before. There are a lot of challenges still left, but I'd like to point out the hardware design aspect in this particular case. All these robots are very sophisticated, amazing amount of engineering work. All the top level engineer software is all working on, but the hardware choice, in my opinion, wasn't quite successful in because these robots are mostly composed of the conventional actuators and transmissions that used in a manufacturing setting, where precision is the predominant goal, which doesn't really work in the environment where you need to handle this unexpected impact, unexpected ground action forces, and precision is not the first priority. I think your balance is a lot more important. Sometimes your force controls are a lot more important. So that kind of like the event was a strong indication of like the lack of the proper hardware for machines that move around outside the factory. So if you know many animals example, this is just one of millions of examples that shows that animals capability where precision, yes, they're precise about something. I don't think they're as precise as a manufacturing robot in terms of the position accuracy. They're precise about something else. They're much better in balancing, much more versatile. And you can talk about many different topics on only on this kind of video, but I'd like to point out the hardware design. So in my career, my career goal so far has been, how do we make a design paradigm shift from this kind of manufacturing robot that is just repeating precise trajectories command without really having the sensors or any common sense algorithms, where you know precision is the predominant goal, and then you can almost solve almost every solution in manufacturing setting using just precise control. But when it comes to situation outside the factories where things are uncertain, that solution start breaking down. So I really been working hard on how to make that design paradigm shift. I would like to briefly introduce many other projects I worked on before, and these are a few representative. So while I'm working on these projects, I kind of gain my knowledge and interest, the understanding of need of actuation and so on. So I'd like to briefly introduce these. The first one is a sticky bot. This is still my favorite scientific project. We ended up inventing things called the directional adhesive. I'd love to talk about this, but it's not the main topic today. The lesion that Gecko utilizes actually is a directional. It's only discovered by Keller Autumn in 2006. And then this robot was actually built in 2006, talking with the Keller Autumn. And we synthetically developed that directionality in our physical embodiment. And that robot really was be able to climb up because of that directional aspect. And second robot is probably the robot that bring me into this running world, biomechanics of running animals, we built this Ice Pro. At that time, was the fastest running robot per body length per second. But nowadays a lot better robot, especially from Berkeley. Third robot is probably the strangest robot I've ever built. This is a thing's called the mesh worm. Is a robot that crawl like a real worm using peristalsis, and we actually use the SMA wire. So there's no hard rigid structure. That everything is very, very soft. So you can squish, you can crush down, it still survive. The fourth robot is actually MIT Cheetah. We're still working on this project. This is like an old video when we first activate and then start walking on the treadmill. We actually implement very different style of actuation, and it was quite successful in terms of energetics. We achieve animals level of cost of transport, total cost of transport. That was actually first time achieving animal level at the time. So that was really exciting, and then we move on to the next step. So I will show you the MIT Cheetah actuation. So this is the things we call the proprioceptive actuation. This is actually the very good example of less is more. If you look at a lot of robotic arm with the force control capability, there's a lot of sensors and additional structures and additional gadgets. This is actually as simple as it gets if you properly design. And then eventually at the end of the day, this is actually the best way to achieve a high bandwidth force control, because there's a stability issue if you're non-collocated sensing, and then you go through all kinds of contact instability issue. So we basically take the inspiration from the Phantom haptic device that initially conceived by the Ken Salisbury's group, and when he was at MIT a long time ago. And we basically learn how to design electric motors and transmissions and structures so that we can design a robotic leg that can control impedance and force and very fast speed. I can talk about actuator for many hours, but I'll just move on to show all these collection of cheetahs. So this is Cheetah 2. This is first time we actually were able to balance in 3D. And then this is probably the fastest robot I've ever built. It runs 30 miles per hour at 60 meters per second. We haven't actually reached the maximum torque. The bottleneck was actually stability. Our controller was very crude and not very good. But we had a lot of fun and achieved something like a steeplechase, like autonomous jumping over obstacle. We're trying to recreate this kind of behavior in more general setting, but vision integration is pretty challenging. At the time, this experiment was pretty much 2D experiment, so it was relatively easy. But it's not very general. You cannot apply this in a random environment. So we moved to a Cheetah 3. You can see the morphology has become a lot more simpler, more robotic, and there's a lot we can talk about why that is. My simple answer is eventually robots or animals are just way too different. It still take a lot of inspiration we can take, and we can learn a lot. But when it comes to execution, we really want simpler design. So we eventually settle down on conversion to this simplest body design, simplest leg, and then that maximize the workspace. If you think about this is a mini cheetah. If you think about like animals in this quadruped world, like many mammals, there's about 700 muscle, and we have only 12 motors. So morphology cannot be similar. A lot of people ask, like, why don't you have a back muscle? It'll be really cool to have a spine. There's a lot of complexity associated costs we have to deal with when it comes to fabrication and control and modeling and so on. So this is sort of like our latest and the greatest design. And then our design actually converged to simpler structures so that we can bang on this robot a whole day long and whole year and didn't even break a single mechanical component. This is the first version 0, the first mini cheetah we built. We didn't have a mechanical failure for about a year and a half. We mostly have some connection issue, the wire issue, but the robot was so well built. We eventually built a 10 of them, and then our sponsor built another 15. So we will be able to distribute this robot to the world. At this point, about 12 mini cheetahs are outside MIT. And we were working on, control algorithms. This is probably the most advanced balance algorithm we worked on. It's called regulated predictive control, and we achieved like a two revolution per second turning speed, and then running speed of 4 meters per second. You can drop from a meter height. We have a lot of fun designing this controller, and we learned a lot about how to design a controller in quadrupedal world and what are the challenges and so on. As you can see, most of these patterns are trot. We tried the bounding, was pretty good, but we realized how versatile the trot gait is. And if you look at most of the quadrupedal world, the trot is like predominant. And animal world, there are differences. Like there's reason why they stay trot on only certain speed range and then move to the gallop and bounding and so on. And in the robotics world, I don't think that's exactly the case. Also depends on what kind of actuator you use, but in this type of actuator, the energetics actually became quite different from animals. We've added cameras. This is probably 2 years ago. We started adding cameras, and then add some algorithms to detect the right obstacles, and adding more intelligence. So we envision to develop a system that can go almost every surfaces, and then distinguishing hard to go through, is impossible to go through, is easier to go through, so it can automatically optimize. One thing I probably don't have time to explain all this, the most important aspect of the actuator design is the really taking care of the total, the operation space inertia matrix. That's actually the most important thing. Like when the foot hit the ground, what is actually real mass? And it's not just a foot, it's not just a leg. It actually involves all the transmissions and actuators. And then a lot of roboticists actually been ignoring this for many, many decades because of the legacy of manufacturing robots. So a lot of roboticists has to buy robots that is actually designed for manufacturing, and then is not very suitable for any contact issues. So we've been having this baggage for a long time. And then we, MIT, we managed to break this. And then that's how we finally achieved to develop this kind of robot. If you have any question, feel free to contact me. I would love to explain this. What IMF means is impact mitigation factor. That is really representing how robot is well designed to handle impacts. We had to develop our own custom actuators and custom electronics to really achieve high bandwidth force control. Because if you really think about the time of contact in the ground, for human cases, running about 150 millisecond or 200 millisecond at most, and then quadrupedal robot like this, they stay on the ground only 100 millisecond. If you cannot control, if you cannot modulate and respond the ground action force during that short period of time, you basically cannot control the robot. So if you look at the graph on the right, blue is the commanded and red is actual. It's not that accurate qualitatively, but this is a time window of 80 milliseconds. So we try our all best to achieve the high bandwidth force control system, and then this is what we got. And then having force feedback through force sensor is actually not a good idea. The same philosophy going back to less is more philosophy. So if you just look at the big picture, like, we've been looking at the Ashimo success is amazing, but after that, we see a bunch of like a hydraulic robot in 2008, but Big Dog, after Big Dog, there's a lot of Big Dog copies and variations came out. So we thought the hydraulics is the way to go until we saw our MIT robot becoming actually successful. And after that, basically quadrupedal robot, hydraulic quadrupedal robot was disappeared. And then all these hundreds of different copies are now on sales, and you can buy in China and US. They're all pretty much following our actuation paradigm. There are a few exceptions, like ETH still use a series elastic actuator, and Boston Dynamics use somewhat hybrid concept. But if you accept those two, most of the quadruped robot, and including bipedal robot like Cassis, are actually following our proprioceptive actuation concept. That's simpler, more robust, and easier to control. I guess the only exception right now is only successful hydraulic machine. I can see. I guess there's a one IIT robot as well, but the most represented robot is Boston Dynamics Atlas, and then has so many degree of freedom. It's pretty difficult to achieve in the electric robot, but that's we're also working on at this point. We'll see. We can also replicate capability using electric motor. I'd like to introduce a little bit of the vision work we're working on. So I won't go through this, but the vision data, you create a point cloud and create a height map, and then you set the goal, you create the shortest path, and then you modify the path so that it's compatible with the robot and so on. So I will show you that demonstration of anytime RRT. It's pretty powerful algorithm. It's not even nearly mature. Our goal was actually behind the luggage, so the robot actually wasn't be able to see it. But any time RRT, you can actually create the trajectory in real time, so you can actually adapt and see eventually where things are, and then react very quickly. So this is an emergent behavior where like a human is interject, which wasn't in the part of plan, but you can actually react and then recreate that. This is pretty like a preliminary result, though there's many algorithm works really well, but we're really happy to see that happening in our robot. And we're trying to connect with this with our maximum capability, like the jumping and running and so on. We're also very interested in like a tele manipulation, because locomotion, I think it can be very autonomous pretty much. I think we're reaching there almost, but the hand motion, the arm motion, and actual manipulation is still really, really difficult and very challenging. So we are so interested in having some human in the loop. So we create this video like 5 years ago, and we're trying to take advantage of our actuation again, because the being high bandwidth system with the force feedback is going to really help us to design a telemanipulation robot that we can possibly remotely control through internet, and we can serve some elderly person in the future when our actually elderly care population become pretty serious. So there's no force sense feedback here. It's still we're using a concept of proprioceptive actuation, but yet you can actually feel the force through our control algorithm, and we're actually making much more complex version of this. And another important thing is the sensor. We actually don't have a really good contact sensor that actually measure force as well, because a lot of good force sensors are very vulnerable to acceleration and then impact and so on. So we develop our own force sensor, and then we can do something that you probably never seen before. This is just the purpose of this demo is actually is nothing. We thought it's fun to recreate the virtual magnet, but the reactiveness and then the robustness of this force sensor combination is can create something you never seen before. This is only possible using our actuation type of actuation and then our type of sensor. So it's really fun. The robot is really fastly, quickly reacting on the force sensing of the sensor we developed. But there's actually no force feedback. It's a little complex to explain. There's actually only contact location feedback, because the sensor actually can detect not only force and also contact location at the same time. So we're trying to augment these kind of capability in the leg robot and then manipulation, so we can make a robot more versatile and then more capable. If you have a time, I would like to briefly explain. Maybe I will just explain in this video. This is, by the way, a video of me picking an apple in complete blind setting. I'm not looking at it. Of course, everybody can pick up an apple in blind setting, but probably not many people take a look at it as a slow motion video. I'll show you in real speed. one more time. This is so fast. There's many action going on, so I would like to see in slow motion. And obviously we're blind, so I'm actually reaching to the apple blindly, and then my fingers are very soft. It's collapsed, it collided with the apple. Apparently at this point, 3 fingers are in contact with the 2 apples. And then if you have some algorithm running some reasonable cost function, you will probably pick one of those in contact. Apparently my hand is much dumber, and then decide not to pick one, and then just try to do action of a grasping, and then unsuccessful because it's unlucky location. And then you happen to make a contact with the 5 apples. Still, if you have a reasonable algorithm, I'll probably pick an apple on the top. For some reason, my hand algorithm has to go down at the bottom. And then, of course, there's a lot of obstacles you have to kind of like dig through. And then you finally made a decent grasping. And then you realize there's a lot of apples on top. So you wonder, I need to maybe have a better posture. So eventually you dig deep to grab probably the worst possible choice of an apple. And then you took it out. The point here is, first of all, I have absolutely no recollection. I have no idea what's going on. I can ask you to try to pick up a key from your pocket and then think about can you remember every action your finger actually did? I guarantee you probably don't remember. I mean, you can try to remember it, but if you do it subconsciously, you cannot remember. Second of all, every single action you see in your hand doing, none of them are that great. It's very, very poor action in terms of cost function optimization setting. Yet overall, whole combination of action, we're really, really reliable. We can do things 1,000 times and probably successful in 1,000 times. We don't have an algorithm that works that well. So the point is, we are so obsessed with optimal setting, optimization. Machine learning is the same thing. Is a stochastic optimization. We are looking at an algorithm kind of different way, and we should be really shooting for like good enough solution in much more complex architecture. I believe a lot of biologists agree with that kind of idea when it comes to biological observation. This is biological observation. And our languages are pretty poor, and even in describing any of these actions, and realize we cannot even communicate properly. Imagine you're explaining this to your friend through the phone, how to make a peanut butter jelly sandwich. If you say spread well, every human being understand that because we have that common sense. But imagine if you write a program to do it, we absolutely no idea how to do that. So a lot of this complex behavior that our brain does that almost automatically, we're not even very aware of it. We're not very conscious of it, and we don't even have a proper languages. And then that's, I think, one of the reasons why we're underestimating the complexity of the physical intelligence, not in this community, but a lot of robotics community are now barely start looking at mixed manipulation becoming another hot topic. But I soon realized how difficult to even describe what's going on in action. I like to bring it up to the community, like when it comes to intelligence, what is intelligence? What is really intelligent? It's really purely based on how we, as human beings, from human cultural aspect. Wow, so the algorithm that beat the best chess player, that's really intelligent algorithm. But nobody will like think that, oh, cleaning dishwasher or bring out key out of the pocket, that's like a smart or intelligent, unless you are actually worked on it. This is purely based on human perspective, because it's easy for us. It's not that hard. If it's difficult for us, that's probably pretty hard. We get easily impressed by jumping or backflipping of a robot, yet we don't quite impressed by grasping a water bottle, because actually it's really, really hard. So when we talk about intelligence, I think there's some sort of like kind of inequality or misconception and bias. I actually wrote an article about it. I think it's very important to understand that there's actually not enough languages and descriptions and representation in the physical interactions, let alone locomotion. Locomotion, I think, is actually one of the easiest tasks compared to like a manipulation. So these are the takeaways. Hopefully I can take it over. I think I'm over time. So I wish I can just move to the discussions. Thank you very much for your attention, and hope we can have a more interaction. Thank you.
Yes, thank you. Are there any questions? I think this will also be a really good segue into our general discussion time. Holger, do you have a question? You are muted.
Thanks very much. Really great. I like your point. Good enough. This is exactly what biology does, because it can't optimize. Biology has to solve so many tasks using the same hardware and using the same, well, overlapping circuits, let's call it that way. It cannot optimize a single task because it would spoil the performance of another. So this is why, well, biology is not really explicitly measuring things in many cases, but it's using some heuristics or some very simple concepts to keep at, say, equilibrium, or keep a certain value or a certain measure constant, something like that. Yeah, but I mean, it made a lot of sense. That was really, really nice. Thank you.
Yeah, thank you. I think the biggest the possible key word here is actually cost function. There's no way to really know what cost function is. I often ask that question to like some computer science major student, like, what is your cost function when you shop, when you do grocery shopping yesterday? You know, like there's in biology, you can really measure everything, and then you're always living with this moving target, and you have just way too many things to negotiate with. You know, but yet our engineering algorithms are dealing with a very well-defined cost function. So the tasks like a locomotion actually is relatively okay to write a cost function, but some tasks are nearly impossible, like cleaning the room, or living well. Like, you know, the nature is evolved to satisfy, survive, but survive could be stochastically, statistically written well, but it's impossible to write a cost function. So when it comes to like complex tasks like cleaning the room, you might think like, can we really quantify all these task success as a cost function or not?
Yeah. Yes, I can see that point. You know, we did once a simulation of gauge stabilization algorithms, and the only cost function we put in, coming from biology, was spent as the minimum amount of energy you could possibly. It was not on precision or something like that. We just said, okay, and that was the result of was an optimized Kalman filter in a sense. The best solution was actually ignore anything that gets you a deviation from less than 5 degrees and kick in only if that value is exceeded. And, you know, something like that, because that's one of the things why biology has come up with some remarkable solutions in a way, because there was in evolution always this one constraint. Whatever you do, it cannot cost a lot because energy is at a premium. And that's actually one of the things, I mean, that's for me one driving point.
Thank you. We also have some questions in the chat. So one from Roger Quinn saying, can we buy the awesome motors?
Yes, the motors are actually the actual electric motor from Minichira is a purchase from China, like was like $80 or something. And if you are Chinese, if you're living in China, you can actually buy them in like less than $30. And then there are many companies, including like T-Motor, sell this similar design. The motor driver though, some are not quite satisfactory. I don't know all the data. They're all copying the Minichira driver, but I heard some rules say that there's some bandwidth issue. Some cannot go too fast. But it depends on application. I mean, we are running and jumping and colliding, so we need really high bandwidth control. But most cases, they are not the case. And there are, you know, if you go AliExpress, you can buy them like in like $300 or $400. And T-Motors also sell those too. So we're happy the fact that our kind of, you know, influences are you know, we're impacting the commercial world, and you can actually buy them.
Excellent. And a question from Kenjiro.
Okay. Hi, can you hear me?
Hi, nice to meet you.
Okay, hi.
Good to see you.
Long time no see. Good to see you too. Thank you very much for your very impressive talk. And my question is the less is more is really interesting. The method or like ideas to sophisticate your robot, right? So, but when you developed the Gecko robots around the 2006 or 2007, you design with the, how can I say, you set the configuration of the robots with the some differential to negotiate the shape of the environment, right?
Yep.
So the so that at that point, you selected that differential linkage or differential mechanism. But if you made the Gecko robot again at present, how do you think you can make the much sophisticated one you can build, or still you can you will select the differential mechanism? How do you think about that?
I think that kind of like underactuated, like, you know, differential. It's good for self-adaptation, like mechanically passive adaptation, because climbing robot, you're at that time is only dealing with the flat surfaces, and typically climbing robot has to be light, so you cannot afford to have too many motors. But when it like I think if I make another climbing robot, I'll probably use a differential again. But when it comes to hand and like versatile, multi-purpose gripper, for example, sometimes that kind of differential passive adaptation give us trouble because we lose the controllability. So, you know, especially in the leg locomotion, like you need to control the ground action force in three axis, and if you have any under actuation, that actually causes a lot of trouble. So we've been avoiding having that kind of passive adaptation, but if you want to achieve one task really well, and then you need to adapt many different things, I think passive adaptation is good.
Okay, thank you very much. And I hope we can meet the directly in some of the international conferences after this Corona disaster.
Yeah.
Thank you.
Yeah, the less is more though, like that's kind of contrasting with the animal. You know, the complexity is just, you know, astounding, and having many muscles doesn't really hurt as much as like having more motors in roboticists. In robotics, like complexity is really enemy. We can't really continue to experiment because it keeps on breaking. And if you think about the whole paradigm different in biology, is grow from embryos and is all made of soft stuff. And even though you got damage, you repair by itself. In the mechanical world, we have to fasten everything, and we can print a lot of things. But if you get damaged, we have to exchange the whole thing. So we're kind of like living in this bolts and nuts era, where less is more is really shining. Maybe in the future we can afford to have more complexity, and then maybe we see more similarity between machines and animals.
Thank you very much for your answer.
Excellent, thank you. I'd like to invite our speakers back to come on video, and really anybody else that wants to join in on kind of the overall discussion. And, you know, I'll kind of maybe start with kind of posing a question. We're making some statements first. It feels like we really had a revolution in legged robotics in the past 3 to 5 years, where we've got this explosion in capabilities ever since maybe everyone saw the DARPA Robotics Challenge and how terrible all the robots were. It feels like we've gotten a lot better at building and controlling robots. But I'm wondering, right, we still fall short in many areas. And kind of, is there maybe a single hang-up, or are there certain areas that we really need to push the boundaries at more at this time? You know, are we looking at, do we need better sensing, better just control paradigms? Do we still need better actuators? Right, I think we might still need better actuators for flying.
I think I want to reiterate what Sangbe said. We need to change our mentality of designing robots. We don't need to think of designing robots based on precision positioning or precision velocity tracking. We don't really need perfect systems, at least when it comes to many of robotic tasks that we can think of, either locomotion, manipulation, etc. I think at this point we are putting a lot of efforts on, let's say, algorithms, optimal control. These methods that try to limit and constrain machine, rather than letting machines and natural body response in the machine to take contribution in the overall process of either locomotion, manipulation, whatever you call it. That's my opinion. I think that mentality has to be changed.
I'd like to add on to that. The precision chasing, yes, was our legacy. A lot of roboticists, even nowadays, are you know, have bias by those legacies. And if you think about like a traditional control designer, control engineer's perspective, precision is everything, because that was the you know, the solution for a lot of manufacturing and automation. Yes, and still, if you want to control, like for example, like old, like a disk, you know, magnetic disk drive, and then you have to control the head very quickly, I think traditional control will work, because that really give you the precision and speed. When it comes to leg locomotion, where I actually have some knowledge, so already precision is kind of like secondary, and then we experience that through our MPC, motor predictive control. Our execution is pretty stable, but if you look at our predictions and what happened in reality, it doesn't really even match. It's much more important to have what kind of reaction do we have, rather than like, do our prediction model is accurate or not. And when it comes to machine learning, that's actually really a shocking transition. I thought machine learning will have a hard time in dynamic system and fast moving causal system. Apparently, machine learning can handle really well stochastic situation, uncertain situation, like, you know, grounded friction change, and you're running on soft ground, hard ground. We have to deal with so many different uncertain situations where traditional control techniques are all breaking down. But the machine learning technique is a lot more stochastic, a lot more noisy, yet it can handle these. So so not only just designing robot has to change, also think about approach of controlling the machine, because these tasks are not actually requiring precision. So there are a lot of things that are changing nowadays, and then mostly positive. We start seeing that, oh, that's actually working. And then maybe traditional method is no longer useful in certain area.
Yeah, I guess it's interesting you're bringing up control. I think what you find in biology quite often is this layered control architecture. So you basically take care of rudimentary processes at a very low level without any higher impact. Only if you want to modify that basic pattern, then there is some sort of drive coming down, and that's true for locomotion or for many other aspects as well. So that's one of the things I think there will be quite some progress if you take that sort of idea into account. And then the other thing is, so it's a modular control, but you have some intercalated architectures. And then the other thing that will probably help is, that is modal control. So if you know what sort of modes you really need to control and may get out of hands in terms of stability, then you can design your system that the sensors are basically giving you exactly the information that is required to control those modes. That's a massive shortcut that gets rid of a lot of computational overhead. And then, of course, the other thing that was brought up by a couple of things, again, the theme of the whole conference so far, I think, is materials and actuators. And that's really a lot of work is required, I think. And that was a really, your talk, Shangmei, was, of course, a very nice example of that. So that actuators matter really a lot.
Yeah, I think I agree. I think we still, there's a lot of challenges in actuation, especially in the smaller scale. I think when it comes to bigger machine, our actuator actually is pretty good. If you look at compare the power density, electric motors are easily 2 orders of magnitude higher than biological muscle. Like easily you can create 100 times more powerful actuator that than biological muscle. The issue is when it comes to small machine, like the Ellie's presentation, like you cannot afford to have that many motors and complexity, and the torque density, not just power density, actually torque density suffer a lot in small scale, and we're pretty much relying on electromagnetic force generation, which is predominant. If you look at the cars, they're all electromagnetic, and I've been relying on that. There are actually a few potential pathway you can utilize electrostatic. If you look at literature, any artificial muscle literature, most of them are actually electrostatic. If you are new, there's a few venue actually we can improve the force density. The manufacturing challenge we mentioned after the talk was actually the critical. The electrostatic, the issue is electrostatic has fundamental challenge where everything has to be close to each other, everything has to be small, where multi-parallel, like a biological muscle, like many very small components should be combined and integrated very well. We just don't have that kind of manufacturing capability. If you're interested, you can Google microhydraulic actuator, which is what I'm referring to. That's actually, theoretically, there's no challenge to make that into as good as muscle. In even small scale, is the integration and manufacturing is something we just don't know how to do yet.
Yeah. I wonder about kind of these kind of control algorithms and like the multi-layer, and like where we might need to be kind of putting more efforts in. If it's kind of more the integration, because we got a lot of people working like at really high level kind of decision making or planning, but almost all of these robots are kind of working with wheeled systems. We need to turn it into actual actions. And then, if we're trying to get more capabilities out of our robots, et cetera, then I would think that we might need to move more towards the biology of more is more, right? More joints, more degrees of freedom, et cetera. And we'll need to kind of find a way to integrate these kind of lower level physical intelligence control strategies into more highly actuated systems.
Yeah, the control architecture is I think is the key. I think is really important, and especially when it comes to machine learning, the main challenge of machine learning, we just don't know what's going on. It's black box some sort. So I've been always the proponent of this building right architecture. You know, the lower level take care of the small stuff, and there's a high level, mid level take care of the organized stuff, like a building like a company structure. The debate though is if you make that multi-component system where each components are developed or trained separately, the connection causes a lot of trouble. So if you talk to many machine learning people, they are saying that no, don't add any human intuition and structure, because that actually outperformed by nothing, no structure. Like the good example is AlphaGo to AlphaZero. They try all their human effort with the human knowledge of the Go game, and then they made AlphaGo. But AlphaZero basically, no, we don't need any human intuition, and then it creates much more high performing. So a lot of successful example we saw actually, they don't want to disconnect training. So they want to connect the input to the output. Even though there's our structure involved, they want to connect all the way so they can train all together. That's actually where the really power of the machine learning come from. We just learned that, like, if you do that, if you develop in each component by manually engineered, which we love to do, we were engineer, we love to tinker. Always they come into problem where, oh, that give me the problem, and then you fix it, but I have to fix it here too. All these like infinite tuning issue, like you have to, it's like in a company, you spend a lot of time communicating between, like, your CEO to middle level and the lower level. You have to fix this, and then you have to send it to find out where the problem is. All these multi-communicative issue can be resolved by just training whole thing as one. Again, the challenge is, like, more you connect, you do, less we know about what the network is doing. That's sort of like a dilemma in my mind when it comes to control architecture design.
Yeah, I think that's definitely a problem. And the other problem is that there are a few people who are trying to implement that, to optimize a system to do 4 different tasks in parallel, because that's not normally, as far as I understand, the way it works, because you can really achieve very high performance for a very specific task if you have sufficient data. And that's it, and then that's great, and we don't understand what's happening in the black box you mentioned. That's exactly the problem. That's why I'm, as a neuroscientist by training, I'm not too keen on that. I still believe in the fact that you sort of can make sense of a neuronal circuit if you look into the connectivity and how this all lines up between sensors and actuators. But in machine learning, that's a little bit taken out. I mean, I guess that's one of the research areas in machine learning, trying to open the black box so that we can learn something from it.
Yeah. So I think we're still thinking about it, but there might be a way to train, so without losing the whole connectivity from sensor to, all the way to the output. We might be able to still train in a way that we can still interpret. Like we can create some network, could be separate or some interject, so we can actually train in a way that we can interpret what's going on without losing the whole connectivity. So usually we have, to see what's going on, we have to dissect. Well, as soon as you dissect, you lose the connectivity. But if you create some branch of some sort of architecture, we can train in a way that we can, like some latent space, we can interpret to translate to the dimension where we can understand. Then we might be able to negotiate this issue. But we're still scratching the surface. This is a pretty challenging topic.
Yeah, it seems like there's been a lot of success lately in kind of bringing in neural architecture into the machine learning environment, kind of preceding what things should look like. And this also kind of makes me think, though, too, if we want a really truly adaptive kind of robot machine, maybe it's going to take 10 to 15 years to train it like it takes a human to grow up.
I have a question. Sangbei, how do you reconcile the control of biological muscle with electric motors?
I mean, great question. I actually don't know too much about how biological muscles are actually controlled. So far we've been pretty much relying on model base and then, position with some stiffness and damper. I've seen some recent work where utilizing machine learning to kind of ignore some modeling aspect. Does animal use some modeling aspect? I probably will say no. I would say the more modern machine learning type of approach is closer to what animal developed through evolution, long-term training, and so on.
Well, we in the animal world have long had these models based on central pattern generators, command neurons, coordinating neurons that can explain all this. And I've always been fascinated with the machine learning models, how you reconcile the two worlds. And for example, with muscle, between the motor neurons and the muscle, you have this process called excitation contraction coupling.
Yep.
And that's been the bane of artificial muscle, is nobody can figure out how to do that right.
Yeah.
And
yeah. I mean, a lot of the neuroscience study shows a certain aspect, but still doesn't answer me how our human body can be so accurate. Like, we're not accurate in position control, but if you look at the sports, like, basketball, or if you look at how cat can handle this, like a dynamic situation, your force control has to be actually accurate, certain behaviors. So if our biological neural network has a sense of dynamics, is it F equal ma? Probably not. There's something else. And then we start seeing the evidence of the recent machine learning community developing neural networks seem to have that kind of understanding of dynamics, far from our F equal ma, I think. So at least I think we're approaching it. I don't know when we're gonna really actually can even assess how close we are, but I mean, muscles are also very, very noisy, so it's very hard to understand what's going on.
Yeah, I mean, that's why for the very subtle controlled or subtly controlled movements, what you actually do is you start co-contracting antagonistic muscles, and that gives you some degree of precision, which you would normally not achieve with a single muscle contracting.
Yeah.
So that's one of the tricks they do. But the other thing in terms of precision, if you think about ballistic movements, which you have a lot, or some periodic movements, it's really this sort of combined forward control feedback loop. So you have always an expectation of what the outcome of your motor action gives you in terms of sensory feedback. And you don't compare, or you don't do the classic negative feedback, but you basically compare against your model. And then you can deal with small deviations and actually crank up the gain maybe, and that altogether can help to achieve quite some performance.
But biological systems can produce behavioral acts called fictive motor programs in the absence of the body. If you cut the nervous system out of the animal and put it in a dish and treat it with the right chemicals, it'll produce behavior. And is there any equivalent to start with in the machine learning world?
Yeah, not that I've seen.
No, no, I don't think so. Actually, I would be very excited to see what machine learning would make of the results that Cynthia has shown us. So the hairs on the wings, they certainly have a function, otherwise they wouldn't be there. So that's a little bit well, straightforward a perspective, but they don't basically, if you get rid of them or disable them, function is not completely abolished. And that's one of the major principles in biology, that you have complementary systems or systems that overlap in terms of supporting a certain function. And they may only affect the system and the performance by like 10 or 15%. And that's about it. And I wonder if you ask a machine learning algorithm to give you the best sort of performance for a system that has 2 different or 3 different inputs, it has to optimize a certain output, what the results would be there.
Yeah, I wonder if the bats had to consciously change strategy too, because I think you showed results that there was like a large number of seconds gap in time to get the insects. And so I wonder if there was a complete kind of rewriting of strategy around that.
I think this is one of the most inspiring things about animals, is that this constant retuning that's so annoying for engineers, like the animals are just doing it, right? They're, oh, so now I don't have any sensory organs on my ventral wings, and they adapt. And that, you know, it's very beautiful and interesting. And in a sense, like that is in itself, that whole process is what a lot of this work ends up studying.
Yeah. Yeah, you bring up a very important point, adaptation, and that's true for the sensory system and other systems, but sensors in biology, they have all one massive problem, and that is limited bandwidth. So you have just a range of a couple of millivolts that sometimes have to encode like 10 to the 12th power in terms of different states, like light intensities. And the trick biology does all the time is adapting many of those sensory systems to the average stimulus intensity or whatever value range they are facing. And then combining that with a closed loop operation, that actually gives you quite a good situation to be in without necessarily knowing any absolute values. And that's what they do a lot.
Well, I think one answer here is that the nervous system has many layers operating in parallel. For example, a central pattern generator, the brainstem, the basal ganglia, the cortex, and any one of these can step in and sort of take over at any given time. And fully understanding how what all those parts are is still to be figured out in my view. And I think the other thing that is just astounding about biological systems is the recent work showing the genetic correspondence between the basal ganglia and the central complex in insects. These systems self-organize using genetic instructions that are equivalent in Drosophila in mice. And in the developmental order in which these genes are expressed, as the system self-organizes, the mechanisms are the same, using the same neurotransmitters and guidance molecules in the two systems. And that is to me the most astounding part of the biological organization.
Are you suggesting that that's convergent? Like that there is some sort of optimal and like, okay, you always should optimize this, and then
it may represent panspermia, and that's probably what it's the best evidence for. This is the work of Nick Strautsfeld and Frank Hirsch. They've had several papers out on this, and it has completely changed my view of how the nervous system puts itself together. And then when you lay learned behavior that uses structures like cortex on top of innate behavior that uses things like central pattern generators, how those operate in parallel and make decisions in very rapid timeframes is something that animals bring to the table that that I think the engineers need to more fully explore. And some attempt to reconcile these two worlds, I think, is a really important target for everybody.
Yeah, I mean, we've seen some examples where they trained with a variety of different situations where, for example, like a friction coefficient is adaptive, like machine learning learn how to adapt different frictional coefficient, or sensor fusion. If you have a sensor A, sensor B, which one to trust? So learn how to trust which one more. But it's all living in this kind of parameterized world, not in the level of this biology where, okay, autopilot running, suddenly your conscious brain come in override, like running in parallel, but like shifting policies in more binary fashion. We haven't seen that yet. And, you know, yeah, is this a complexity of an architecture is still lacking in machine learning because they still want to connect, train, whole thing together. So they had a hard time dissecting or adding layers, like, you know, the animals that run without forebrain kind of structure is hard to create manually because they want to train whole thing together.
So Sangbei, do you have anything in your control models that represents, for example, like the cerebellum?
No, not at all, because we've been developing balance control. We're barely simulating small part of the cerebellum, not forebrain. Oh, did you say cerebellum?
Yeah, cerebellum.
Yeah, it is a small part of cerebellum, but there's, you know, human has a multi-level higher, right? So, you know, what most controller engineer doing, and including us, are, you know, basically brainless chicken walking around. But when it comes to vision, things are suddenly very complex, right? You have to negotiate vision, perception, and decision making. Should I run around or should I jump over? That kind of decision is also require a lot of planning. And so in my opinion, the machine learning is kind of taking over that kind of like a low level part, cerebellum part, but I have no idea how to go beyond.
So yeah,
I wanted to chime in because Joe, some of these questions you're raising, I think, are really interesting and relevant to some of the work we've done lately. How do you integrate this CBG command neuron low-level invertebrate control system with some of these other questions, right? How do you tune the whole system? How do you modify it from, you know, with information from higher level control centers? And, you know, based on actually some of the work that you've done, we've put together various leg controllers that have this neurobiology structure. And then we came up with functional constraints on the parameter values within the network, which then you can optimize around if you want, or you don't even have to, such that then you can have a functional network that does what you think it should do, tied to the anatomy that you observe in the animal, but then you can apply machine learning techniques on top of that if you want. And now you have a starting point where you have some actual structure, and then you can just turn some knobs until it does what you want. And so, you know, it's our approach is maybe, you know, it's our specific way of doing it. I'm sure there's lots of different valuable ways to do it. But I think it's a critical question. How do you leverage what we already know about how animals solve these problems? But then how do we apply the best of what's out there now to further refine it? You know, so maybe you and I can talk about that more later.
And one other thing that animals bring to the table is a phenomenon called neuromodulation. And when you take a central pattern generator and apply different neuromodulators to it, it changes the strength of the synapses in strange patterns. as well as the dynamical properties of the individual neurons, such that you can sculpt out of the same physical network many different connectivity patterns and little mini networks that can produce different behaviors and subcomponents of behaviors. And coming to grips with neuromodulation is something that I think that the engineering side of the world needs to come to grips with, because it really has completely changed the way we think about how the nervous system operates.
Well, we have a paper in review right now. Actually, if you want, I can send you the draft and you can tell me what you think. Where we model octopaminergic descending pathways that act on local pattern generating networks based on identified descending neurons. And this does exactly what you're saying, but in a robotic system with no direct input from the user. You know, it's local feedback reinforces the neuromodulation, which reinforces the behavior. But then if you send us a brief descending signal, you can alter the behavior of the network, and then you will transition from stepping to not stepping, or vice versa. So yeah, we are really trying to tackle those questions. I agree with you. Those are super critical to actually building something more functional.
Yeah, so I mean, that's true. So neuromodulators are really a big asset for biology, that's for sure. So we show that for sensors. So neurons that are processing optic flow, if you supply them with octopamine or an octopamine agonist, they change their input-output characteristics and push it into the higher dynamic range, which makes sense. But the same neurons are also depending on the locomotor state. So when the animals are resting, the dynamics are in the low range. When the animal is starting to move, then they can actually analyze way faster changes in terms of visual motion. And this is all very clear, and that has been shown in many groups, including Michael Dickinson's group and so forth, where you can test individual neurons, change the locomotor state, and that's all depending, or greatly depending on octopamine. And that's really amazing. And we should also remember that octopamine does not only have an impact on the neuronal processes, but it is also switching metabolic states in the animal as well. So they burn different energy when they're flying as opposed to when they're walking. That's probably for walking insects, well, when they're resting. And that's probably the same for walking insects as well. Neuromodulation is a massive point. And
yeah, I should also point out that we are thinking about things like the amines, octopamine, histamine, et cetera, stuff like that. Yeah. But there's this other category of neuromodulators called neuropeptides. And these are short chain amino acid sequences of 4 to 11 amino acids. And when you think of the fact that there's like 30 different amino acids involved, the number of possible combinations of these individual neurotransmitters is mind-boggling. And the first one of these was called scotophobin, and this was discovered in the 60s, and it was a neuropeptide that caused animals, they were originally described in goldfish, to avoid the dark. And it turned out if you took the neuropeptide from the goldfish, sequenced it, and then synthesized it de novo and injected it into mice, the mice wouldn't go in the dark. So we have huge aspects of our behavior that are controlled by these very, very rare and seemingly insignificant molecules that can change the whole show. And I think any engineering model has to come to grips with the fact that there's that level of control out there.
So can I?
Go ahead.
I was just going to ask.
I was going to do just one quick, I want to keep this discussion going, but I also recognize that some people have limits on their time, and I want them to feel free to duck out whenever they want, you know, say bye in the chat or just wave. And yeah, so yeah, this has been great. Thanks everybody who stuck around so far. And yeah, feel free to stick around longer and keep chatting. Go ahead, Kitty.
Thanks. Can I ask, so when I hear biologists say like, oh, neuromodulation changes the whole thing, from an engineering perspective, like we can write as many subroutines and have as many circuits, like, virtual circuits, they're almost free. Like, is it a specific advantage that they're reusing the same sets of circuits to do different things? Would it be better for us to model them like, oh, okay, now this is a different circuit when there's dopamine or whatever other one? Like, why is that so important?
I think all of the above is important.
Yes. Well, I think that the nicest example for a neuronal network that is under heavy neuromodulator control is the stomatogastric ganglion. Most of the neuroscientists will know what I'm talking about. So we have a network of some 100 neurons or so. I don't know the exact number.
30.
Sorry?
30, yeah.
30 only. Sorry about that. So that's a massive difference. Well, the number of neuromodulators in the same network is higher. Now, why would you do for a very simple thing? So stomatogastric ganglion is concerned with digestion, right? So it needs to create a pattern of movement to get the most out of the food. Why would you use such a sophisticated control mechanism? Well, if you have 30 neurons and as much neuromodulators, you can produce whatever pattern you want with your stomach, right? And then you can adjust what the stomach is doing to whatever you eat. So you get a huge amount of flexibility in performing a certain function. And I think that's one of the major points. It's basically how you tweak the individual components so that altogether you can achieve a certain function very good. Well, the stomach has got one function only, and that's why it would work really well with, neuronal networks as well. So I think.
Well, one thing about all arthropods is they live in a box, and in order to grow, they have to molt. And a lot of these peptides are active because when a lobster molts, it actually molts out the lining of its stomach, which involves the stomatogastric control. And so there's many peptides that are involved in things like that we would never otherwise think about. They do have to regurgitate. They can eat a broad variety of substrates. So they probably have individual motor programs for each one.
Yeah.
Then there are also glands, and these are controlled by neurons, and those are secreting substances into the digestive system to mediate digestion. So there's plenty of opportunities for different degrees of freedom just in a stomach.
Right, but I feel like that didn't, I think Katie's question is still somehow beside these considerations, because a robot is not constrained by body size or number of neurons or anything, right? I mean, we can download whatever program we want from an Amazon server running in the desert. So this makes perfect sense within the context of an animal. But if I want to make a robot, is there any advantage to using the same network? And I can just write 50,000 different programs and load in which one I want. Is that related to your question, Katie, or am I totally misunderstanding?
Yeah, no, Nick, you and I are asking the same questions. I'm learning a lot.
Well, for my money, the thing that really distinguishes robots from animals is that animals integrate their power supply with their actuators. They have mitochondria in their muscle fibers, so they don't have these funny power requirements that robots have. And I know as someone who builds underwater robots, the three biggest problems in underwater robotics are batteries, batteries, and batteries.
Yeah, above water too.
Right. I'm being told we need to move the discussion to the main room, just in order to make me the host and keep this going. So let's all, I think, close the breakout rooms, and we'll meet up again in the main room.
I think I got to run actually, but this has been a wonderful conversation.
Okay. Yeah, same here. So thanks very much. Bye.
Okay.
Soon, and I just wanted to make sure that you guys can talk on, and I will make Alex the host, and then you can go on.
All right,
Thanks,
thanks.
Paul.
Yeah, no problem. Have fun, guys. So Alex, now you're the host, so everything should go on perfectly. You're muted right now.
Perfect.
So I think what the conversation we're having in the other breakout room makes me wonder, though, is like, because animals are so different with their mitochondria and their like neuromodulators, you know, I think it's still always interesting to find new ways to learn from them for engineered devices. Because I don't want to conclude what, you know, like I don't want to give up and be like, oh, they're just too different. We'll just ignore these like very parallel problem solutions.
And are the okay, so my response to Katie and the question about why don't we just have a million different different basically subroutines and we just bounce around. It's basically a hybrid system. You can do that, and people, you know, people have done that. Our experience long ago was that was brittle, and that you're just jumping around, and you could be jumping quickly before you actually get anything done. And now, oh, the sensors say, oh, we should do that, so we jump over and do that, and it's just a mess. Where animals don't seem to have that problem. Animals aren't, and it goes back to machine learning versus using actually mimicking nervous systems. In my mind, also machine learning is fantastic. It will, it's garbage in, garbage out, unfortunately. But if you actually train it properly, it can actually work really well to a point. But again, when things change a lot, now you have a problem. So that's my argument for going with mimicking nervous systems, even though motors are different, everything, so much is different. I think there's a lot in the details of the nervous system control that actually is appropriate, but that's my opinion, and I've been wrong before.
I think building on that.
I don't know if Songbai Kim's still, I don't know if Songbai's still there or not, but long ago, I said you're going to have trouble getting the cost of transport of an animal if you didn't put tendons in, and you proved me wrong. So that was my opinion long ago, so I got that wrong. So I admit that, and congratulations, by the way, that was a long time ago, like 10 years ago, that you published and showed the cost of transport. It was fantastic.
Yeah, I think one of,
yeah, go ahead.
I was going to say, building on that, I think one of the advantages with kind of the neural system, neuromodulation, is the more seamless transitions between things, as well as kind of the slight adaptations or partial adaptations that might kind of intelligently emerge from these systems. And so by kind of having the multifunctional subgroups kind of all interacting with each other, then you can get transitions in the different subgroups at certain times. And I guess that's kind of one of my theories for in investigating this gate control stuff, is that kind of these gate transitions, et cetera, will kind of more seamlessly emerge from kind of a neural controller with the right structure.
So is there evidence of this where like something you learn under one neuromodulation set like makes it easier to learn something else in another neuromodulation set? Like in biology, I mean, like, is there an example of like, oh, because this was learned under these conditions, now you can go back to that under different conditions?
I don't know.
Okay, well, maybe that'll be something new to come we'll get to see in the future.
Well, one point I'll make out about biological networks is that I was Al Silverstone's second postdoc after he had figured out the wiring diagram of the stomatogastric ganglion. And at that point, we truly believed that if you knew what the network was, you would know how it worked. Well, if you look at that network, it's unintelligible. There's no obvious function in it at all. And the dynamics and the strength of the synapses change all the time, even if you've got the nervous system cut out of the animal and in a dish. As the titers of some neuromodulators change, it becomes a different network and has very different properties. What I found was really helpful was to use perturbation analysis, which is how they analyze circadian rhythms, where you give them randomly placed stimuli and construct phase response curves and do stuff like that. That made it very clear how the thing was working. But prior to that, before perturbation analysis, I think these networks were largely unintelligible.
All right. Well, feels like the conversation is winding down.
Thanks, Alex, for organizing a workshop with such a fun conversation.
Yeah, thanks everybody for showing up. I hardly had to do anything, so.
Thank you so much.
Yes, thank you, Singbai.
True.
Thank you, Jiro.
Thank you very much, Alex and everyone. See you.
Thank you.
Thank you.
Hey, Joe. Always good to see you. Glad to see you. Glad to see you hanging in there. Still doing the work.
Well, I try.
All right, see you tomorrow.
See you, Roger.
See you, Alex.